just fix this thing. Say it again. No, I think it's fine. Yeah, I'm going to come this way. I don't know why everybody's sitting on this side of the room. Is there some reason? Light, okay, yeah. Maybe I'll stand on this side of the room as well. I might sit though, because my ankle started hurting a lot. Let's see. We're online or? Okay. All good? Yeah, okay, you're gonna move that. You can do that while I start talking. Okay, we're in lecture 4 of computer architecture. We're going to cover memory-centric computing today. We covered a nice overview of a lot of things in computer architecture with a focus on memory. Today, we're going to go a little bit deeper into how we can do processing in memory. Does that sound good? Okay. Oh, that moved. Yeah, maybe I need to do this to begin with. Okay, so we already motivated why we want to do processing in memory, so I'm not going to do that again. For performance, energy, efficiency, sustainability, as well as hardware cost reasons, it makes sense to move the computation capability or enable computation capability somewhere else other than the CPU, other than the computation units that are currently far away from memory, basically. Put computation units somewhere else as well. And one of the reasons was energy, and this is an example that we covered, so I'm not going to cover it again. And we said that if we want to fundamentally solve this problem, we probably want to take a paradigm changing approach, which changes the paradigm to doing computation in other places as well, especially in memory, inside the memory chips. So we're going to look at that a lot today. And this reduces data movement that happens in the system, which we quantified with multiple studies so far. There will be more of that. And it fundamentally eliminates the data movement in some cases, actually. You don't go out of the DRAM chip if it's possible. And this way we can compute where it makes sense to do so without moving data as much, where the data resides. And we want to make computing architecture more data-centric. So this is processing in memory or memory-centric computing paradigm. And we've seen that there are many places where we can do computation. In this lecture, we're going to especially look at DRAM. And we're going to introduce some of the DRAM's operational principles. And we're going to take advantage of those operational principles initially to actually perform computation. But keep in mind that a lot of things that we are going to describe are also applicable to SRAM. We could also cover that. Also storage, we're going to cover that actually a little bit. And also sensors. Basically, all of these technologies over here that are there to ingest the data through sensors and also store the data are also capable of doing computation. And we're going to look at 2 fundamental ways of enabling computation in any place, processing using memory and processing near memory. And both of them are applicable to all of the different technologies in the end. Although our focus is going to be on DRAM, DRAM is very special because that's the main memory technology today. SRAM is interesting, it's on chip, but it's not that large. So you don't have a lot of data, although it does make sense to do processing inside the SRAM as well, if you actually have a lot of cache resident workloads, for example. And there's work in that area too. Storage also very interesting, especially with very increasingly large data sets. So this is a self-fulfilling prophecy right now, since everybody's sitting here, everybody's coming and sitting on this side. And because I'm on this side, nobody's going to that side. So I'm going to sit also because I don't want my ankle to die. I want to be able to walk still. I normally don't lecture while sitting, but I have done that when my ankle was broken and I couldn't stand. So I'm going to take the liberty of doing that again, if you don't mind. Okay. So we've seen this slide before. Essentially, we want to process inside memory, and we've already covered a lot of questions over here that I'm not going to cover again. You remember this. Actually, we're going to cover a lot of the questions here, maybe not all of them, during this lecture partially, but also in the next lecture next week. Maybe 2 more lectures. I don't know yet. Let's see. Depends on your questions also. So today we're going to especially focus on how do we design the compute capable memory and what kind of benefits you can get. How do we perhaps rethink some of the algorithms to take advantage of the compute capability inside the memory? So we're going to look at especially those questions. Maybe we'll not look at every single question over here, because you may need to imagine some of the things as well, right? So what is the interface, for example? I'm going to talk about the interface also, actually. So we're going to cover a lot of things at varying level of details. I should also say that this is not a new idea. There are many people who have walked this earth that are quite smart, and that includes computer engineers and computer scientists. There are some people who in the 1960s imagined processing in memory. These people unfortunately don't get as much credit. Some other works in 1990s get a lot more credit for some reason. But these people, in my opinion, should get the first credit because they're the ones who envisioned the idea to begin with. Somehow they were forgotten by the people in 1990s. And I think a lot of us rediscovered these works in 1960s because those 1990s works don't talk about these. I don't know why, whatever reason. Maybe they didn't have access to internet. That's possible. But anyway, this paper, it's a short paper from Kautz that discusses the idea of putting logic next to memory structures. We're going to cover that. I'm going to call this processing near memory or logic near memory. But we're going to cover this after I cover something else, which is fundamentally different, as you will also see. Okay, so it's good to look at these papers. There's another paper, which is essentially proposing something very, very similar, putting logic next to memory. And they argue that this is a cost-effective approach for doing computation going into the future. This is by Harold Stone. How many people know the name Harold Stone? Anybody? Rahul, you don't know? Well, he of course knows because he sat through this lecture. Rahul finished his PhD recently on October 1st. He defended his thesis, so he's sitting there over there like a happy clam, as you can see. But Rahul is always a happy clam, so that's good. Okay, yeah. So Harold Stone is a computer architect who worked for IBM for a very long time. And he actually did a lot of interesting work. This work he did while he was at the Stanford Research Institute. And he has a very nice computer architecture paper that's also forgotten. People like forgetting things these days. But it's a very nice high-performance computer architecture textbook, which is very fundamental and very clean, I think, and very technical. Okay, but not always the technical books win. Okay, let's move on. So this is also a processing near memory approach. Okay, you should also ask the question, right? Why are we examining this today if people have examined this proposed in 1960s, right? We're talking about 1960s. And then later people looked at it in 1980s, 1990s, 2000s. And then more recently, after 2010, there's a much more intensified approach to enable memory-centric computing or processing in memory. I use these interchangeably. Basically, whatever we discussed last time, we have nowhere to escape in a sense. Today, we're in a much different space in terms of applications and systems. Data access bottlenecks have been exacerbated much worse over the course of last 60 years. And one of the reasons is because logic technology scaled really well due to Dennard scaling, Moore's law, etc. Transistors became much better and logic technology became faster, more efficient, but the memory technology did not scale as well. And interconnects did not scale very well. So communication became a much bigger bottleneck compared to 1960s, 70s, 80s, 90s, 2000s, 2010s. We're in 2025. And this is getting worse, basically. And we've already seen the effect of energy and power and data movement energy dominating computation energy in multiple ways. And today also, we need performance, energy, and sustainability all at the same time. So in 1960s, nobody cared about sustainability. People who were talking about climate at that time were, let's say, maybe they were being poked fun at. They're still being poked fun at by some people who don't understand science, but that happens essentially. But essentially today, sustainability is a much bigger issue that is hopefully affecting the design of computing systems. And today, we want both performance and also energy improvements. We want to reduce energy and improve performance at the same time. We don't want to be improving performance at the expense of a lot of energy, basically. Unfortunately, this is ideal, right? I'm talking about an ideal. In real life, today people are a bit crazy about improving performance at the expense of everything that's happening, and especially hyperscalers. I hope this will cool down and people will get to their senses at some point. But ideally, at least, we should be really improving performance, energy, and sustainability all at the same time. Otherwise, we'll be in deep trouble very soon. If we're not in deep trouble, your kids will be in deep trouble, and I don't know if they will love living in this world. That's really a terrible thought. But anyway, maybe that's why people don't have kids anymore. Which is a good reason, actually, not to have kids, frankly. But again, essentially, jokes aside, we want to actually improve all of these metrics today. And these metrics, some of these didn't even exist in 1960s. Energy, for example. People didn't think about energy. Power, they thought about how to power this huge computer, but energy was not a big concern. Today, energy is a huge concern. At that time, cost and performance were the biggest concerns. Today, we have energy, we have sustainability, for good reason. Okay, and on the other hand, we also have difficulties in memory technology scaling that we have seen last time, yesterday, and we're going to see more. Essentially, memory technology scaling is not going well. We have issues like RowHammer, RowPress that we discussed, and these issues can be solved by putting computation inside memory, as we have seen also yesterday, which is already happening in industry. So that's good. Industry, things are happening in industry because of these reasons, and we're kind of squeezed in the middle. Technology at the bottom is pushing us to do something different in terms of paradigm, and applications and systems and the requirements from the users, at least the smart users, are pushing us to do something different from the top. So we're kind of squeezed in the middle. And also at the same time, we have some emerging technologies that we will hopefully discuss today, or if not in the emerging technology lecture. These can enable new functions in memory. Some of them are capable of, for example, matrix vector multiplication using analog computation capability because of the way they are actually designed. This is actually fascinating. This was not the case, for example. People discovered some of these things in 2010s or so. So we're going to talk about that first, not the emerging technology part, but about the DRAM part. Okay. So this is just to jog your memory. We discussed RowHammer. We discussed the scaling aspects. We looked at some papers. And we argued that adding computation capability inside memory or near memory helps these things. And we talked about some papers, and we talked about industry papers also that actually added computation capability inside DRAM to solve issues like RowHammer. This is just to jog your memory. We're going to see more of that later, and this is being standardized. So this is actually important to think about because I had the slide much before this industry stuff came along. Now industry stuff supports that slide also, right? Basically, I always argued that we need intelligence inside the memory, we need computation inside the memory to solve these issues. Now I can show you chips that have computation inside this memory to solve these issues. So that's good. So industry, in my opinion, is doing something better than before by thinking differently. And you can read more papers if you're interested, as we discussed, right? Okay, I'm not going to talk about this. Now today, so we looked at how to solve some of the scaling issues with computation inside memory. We're going to see more of that later on, and also the other approaches to solve RowHammer type problems. But today, we're going to look more into how to actually enable computation in memory. And I call this processing in memory to accelerate applications, basically. And we're going to look at two different approaches. Fundamentally, there are really two different approaches. I think there are no other approaches that I know of. You can combine the approaches, of course, in different ways. But we're going to start with processing using memory, and then we're going to talk about processing near memory. And I'm going to describe the approaches essentially. The terminology in this area is horrible. People call processing in memory some things. They call compute in memory, and they mean processing using memory, actually. Sometimes they call near memory processing, which is okay, I guess. So I want to just clear up the terminology. And I wish everybody used a clean terminology. Yes. Yeah. So for me, processing in memory encompasses everything, near and using, basically. Yeah. This is what people called logic in memory in the past, right? But logic in memory can be done near or using, essentially, if you think about it. Yeah. That's why I think this makes sense. Like you do processing in memory, essentially depends on how you envision memory also, right? Okay, but okay, there are two fundamental ways of doing computation in memory. One is near. Now, what does this mean? You take memory, you take logic. Today, these are designed completely differently. We have some computation units that are designed using a logic process. You use logic compilers, logic flows. You actually have fabrication technologies that are actually optimized for logic. Like you design a processor and optimize the logic. Basically, a processor, a CPU, for example, or a GPU, or an MPU, neural processing unit, is mostly logic. There's SRAM, but SRAM is actually compatible with logic, essentially. And that is manufactured using a special logic process. Let me finish this, and then you can ask. And then memory, if you think about most memory today, that is designed in a fundamentally different way. The design of memory, DRAM, flash, and some of the emerging technologies, not all of them, are actually done completely separately. It's done by different people for sure, but also different tools, different compilers. There's a memory compiler that's at least the DRAM things that's very different, and then also different fabrication technologies, right? DRAM, for example, because you don't you need to design the capacitor and you need to make it as small as possible. The fabrication technology that you need over there is fundamentally different from something that's optimized for current modern transistors. So these are designed completely differently, right? So processing near memory says, design things as you are doing today. Memory separately, logic separately, but put logic closer and closer and closer to memory. Now this could be, today things are far, right? You have, let's talk about main memory. You have main memory, DRAM, and you have processor, and that computation unit inside the processor is far away from the main memory. Put it at least to the main memory controller. Now you're processing near memory, right? Nearer at least, right? You could of course be farther also, but we don't want to do that, but you're nearer. And then put it maybe inside the DRAM chip, but next to each bank, right? Now you're even nearer. Put it next to each subarray, as we're going to see later. That's each bank is composed of subarrays. Now you're not putting it next to each bank, you're putting it next to each subarray, even closer to the memory arrays, right? Put it next to each cell. Now you're even closer, right? At least to that particular cell, you're closer. So that's the idea. You design logic and memory separately. Or if you have 3D stacking technology, as we will see probably in the next lecture, you have logic layer, you have memory layers. Put the processing units in the logic layer, and then you're closer, right? Again, maybe not inside the DRAM chip, DRAM die, but you're still closer and you have some advantages, which is high bandwidth, low latency access to memory. So that's processing near memory. Let me finish using memory and then you can ask your question. That's probably a good time, unless your question went away. Maybe it'll go away, let's see. Okay, so that's processing near memory. You do business as usual mostly, design logic as you do today, design memory as you do today, but integrate them closer to each other. That's easier to adopt, easier to do in general. That's why industry is examining this much more aggressively today, because it's an easier path. Processing using memory is fundamentally different. And this is what people envisioned in the 1960s, processing near memory. Processing using memory is different, fundamentally different. It's also, I think, more disruptive. And also, it was not discussed, at least as far as I know. Hopefully, someone will find some earlier papers. It'd be great to see that. It was not discussed until 2010s. So basically, processing using memory says you have logic and you have memory. Forget about logic. We don't do logic. We have memory. We designed this memory. But this memory has some operational properties, analog in nature, that also enables to do computation. Yes, it does memory, it does store data, but some of these operational properties of the circuitry also enable it to do some particular type of computation. So use the memory to do computation, to do processing. That's why it's called processing using memory. And we're going to see that today. So for example, you have DRAM. DRAM is designed in a particular way, and the chart sharing capability of the DRAM enables computation capability. Right? You don't add extra logic. You can, now that becomes a combination of processing using and near. But you don't add extra logic, you just use what happens with memory to do the computation. Make sense? So these are two fundamentally different approaches to processing in memory, and they could be used with any technology. I'm going to actually have a taxonomy soon. It could be used with DRAM, it could be used as SRAM, it could be used with flip-flops, it could be used with tape, could be used with hard disks, could be used with flash. All of them, that memory can change basically. Okay, you had a question? Yes. Go ahead. Yeah. Yeah, makes sense. Actually, I agree with that. Oh, okay. So let me take the SRAM. So we're not going to focus a lot on SRAM in this lecture, but there are a lot of papers on that, and that's good that people are doing research. But certainly, doing processing near SRAM or using SRAM, yeah, sure. It's both good, basically. Certainly, we should have that. No question about that. And in fact, we should have it in any technology, in my opinion, because any technology will be capable of near or using. The second is FPGAs. Are they considered processing in memory? So it depends on what part of FPGA, right? FPGAs have lookup tables, and lookup tables are a mechanism of using memory to actually do computation. Yes, that part, yes, but not the maybe not everything in FPGAs. Does that make sense? So lookup table-based computation is fundamentally about assuming it's implemented with memory structures, which it usually is actually, you look up tables. It's using memory structure to do computation. So what's the lookup table? Basically, if you want to compute A plus B, for example, you can input a combination of A and B, and that is the address, that's your address essentially. Let's assume that they're both 4 bits each, right? A and B are 4 bits. The combination of them are 8 bits, right? And then you have 2 to the 8 entries. Each entry has the result. If A is this value and B is this value, this is the result of addition, right? That's a lookup table. You don't need logic to implement addition. You need a lookup table in that case. And that's definitely processing using memory, right? No question about that. But FPGAs don't exactly work that completely work that way. Okay, and we're going to see actually lookup table is computation also in DRAM, and I think there's a lot more work to be done in that area. If we can actually implement better lookup tables inside the DRAM by adding more capability to take advantage of DRAM as a lookup table-based computation engine, there's a lot of potential. It's good to think about potential research directions as well. Okay, so I should also say that these can be combined. You can have processing using memory, and then you can add extra logic next to it. That's fine, perfectly fine. That makes you more capable. Fundamental differences are, if you do processing near memory, you design logic separately. So the logic can be much more, let's say, sophisticated, right? Whereas processing using memory, because you're using the operational characteristics of the memory technology and the device, you're limited to what the device and the fundamental technology can fundamentally do. And we're going to see that in DRAM, for example. Unless you change the structure of the DRAM, it's going to be limited to doing bitwise computations, for example. But some other memory technologies will be able to do analog multiplication, matrix vector multiplication because of their structure and how they're designed. Does that make sense? Okay, so let's jump in. So this is a pictorial view of different way, the same thing I said over here. But you can see that processing near memory can happen anywhere as long as you have additional logic, whereas processing using memory is really using the cells inside the subarrays to do computation. Okay, so this is my broader taxonomy. I gave you nature of computation, but then there's technology also. Which technology do you use? There are many potential technologies. What location in the system that technology is instantiated in? You can see that there could be many places again. And in the end, I think a tuple of these 3 determines your PIM type. So you can combine processing using DRAM in main memory, for example. That's what we're going to look at, for example. But you can also do processing using SRAM in your caches, right? In your L1 cache, let's say, or L3 cache, or L4 cache, right? And you can actually have many different PIM types in a system. Processing near DRAM, processing using DRAM, processing near SRAM, processing using SRAM. Today, we don't have any, let's say, at least in the general purpose market. Okay, so we're going to look at also some real devices, not just now, but today, actually, you're sitting here, and there are actually a lot of things that people have developed, like 3D stacked memories. We're going to look at that. Micron had this automata processor early on that did some deterministic finite automata computation in row buffers. We're going to look at that. This is the UpMem engine that was designed by a French startup in 2019, where they have actually, these are all processing near memory engines, by the way. They had a processor, general purpose processor next to each bank. These are real chips. Actually, you can find it in our lab. We have 3 of these big machines. They're very loud. You can do computation, you can do programming. You're going to do programming of that, actually. There are also chips that we don't have, or many people in the world don't have access to yet, as far as I know. Samsung SK Hynix, and Alibaba, they've designed their chips, DRAM chips, where there is processing capability next to each bank. So these are all real. And also there are other things that look like this, which is, this one over here, where you can do, you have an FPGA essentially over here. And next to each FPGA, there is a lot of memory modules that are put, and this FPGA aggregates data from these memory modules and that does processing, so that the data doesn't need to go to the CPU or GPU that's far away, right? So you could be processing, this is essentially processing near memory also, right? Processing in an FPGA near memory. Okay, so there are a lot of prototypes that people have been developing, as you can see, and there are many other experimental chips and startups. And this is, our focus is still DRAM over here, right? There are also chips and startups that work in processing in SRAM or flash. Okay, and people are actually developing, this is SK Hynix, for example, they're developing prototypes where they can do processing in an FPGA card next to high bandwidth memory, very similar to what I showed you earlier. So there are papers that major manufacturers are also writing in this area. So today is very different from like 5 years ago when I was teaching this course. Now you have these pictures and they're real, and people are actually examining this idea. They're publishing papers in top conferences also. CXL is Compute Express Link. It's essentially an interface, an interconnect technology, and also an interface standardized that enables you to offload computation somewhere else other than the CPU, assuming your CPU implements that interface. Yeah, anyway, it's not that important. We're not an industry. We're not going to throw these words to you, but some things it's good to know. Okay, so we have a lot of things that are covered in this PIM review, so I'm going to keep referencing it. And I should also say that before I start the depth of the material, if you're really interested in this, there is a PIM course that we used to give. We may start again at some point, let's see. But this covers a lot of the real industry machines. For example, I don't know if I can read it, real world PIM, for example, right? From Samsung, from SK Hynix, from Samsung, other companies. So if you want to really know about these real systems, there's a lot more coverage. In this course, we're going to talk a little bit about it, but our goal is to really build the future, not today. So we're going to discuss the takeaway lessons from some of those real chips and focus on what we can do better in the future. But there's a lot more information about these systems in our processing in memory course. We also have an SSD course that's probably more relevant when we discuss that SSDs. So we also have very cutting edge tutorials. So if you really want to know a lot about this, there's a lot of material online starting from 2023. This is all on YouTube, all public. And there are some industry presentations also about their machines from IBM, for example. They do a lot of work on phase change memory-based analog processing in memory. Also from Samsung, Alibaba, SK Hynix, you can find them online. I'm going to do this. And this is the last one, I think, at ISCA. Okay. Yeah, there will be another one, hopefully, at HPCA this year. Next year. Okay. Okay, so we're going to cover processing using memory first. This is a longer term. And sometimes when I give this lecture at different places, I always ask them, which one do you want to cover first? Or if we don't have time, I ask them, which one do you want to cover? Because we have time for only one of them. Usually people pick processing using memory because it's a longer term and more, let's say, harder to make work type of approach. But sometimes if you give this talk in industry, they like processing near memory and they don't want to touch anything like processing using memory. Those are the backward-looking people. I'm just kidding. Yeah, but certainly, yeah, business as usual people, I should say, not backward-looking. Because backward-looking is actually designing something that's older and doing it again and again and again. It's boring as opposed to improving. Okay, so our mindset will be actually accelerator. Basically, we're going to treat this memory as an accelerator, even though it may have complete general purpose computation capability. And the reason is today we're designing a lot of accelerators, right? We know how to offload computation to an accelerator. Not so easily sometimes, but at least we have developed some infrastructure to enable that. It could be much better. It could be much more seamless. For example, you write a program and automatically parts of the program get shipped to the appropriate accelerators. We're not there yet. It'd be nice actually to do that. I think it'll take some time for us to get there. Today, people still need to program accelerators carefully so that you can figure out what goes to which accelerator, right? Now, the idea of processing in memory can be used as an accelerator also. This could be an accelerator of sorts. it could be good at accelerating different things. The question is, what kind of different things? Basically, that's the question what we're going to look at. Okay, so memory is similar to a conventional accelerator. Right? This is a little bit different from a distributed system type of model, where nothing is an accelerator. Everything is an equally capable agent. And you don't offload computation, but you actually program in a way such that everybody contributes to the computation and seamlessly computation happens, right? There is no central unit. So that's actually a very different model, very difficult to do today in today's programming models. Accelerator is easy because it assumes still CPU is the king, right? Kings are very hard to get deposed, as you can see, right? People have figured it out over history. Kings turn into something else. Here, CPU turns into something else. Even though it's not doing most of the work, it's still the CPU, right? There's something to be said about human governments this way as well, right? They're not doing any work, but they're still the king. Yeah, okay, think about it that way. That's probably more approachable. They're still making a lot of money though, you know? Okay. Okay, so we're gonna look at processing using DRAM. In this case, our nature will be using, technology will be DRAM, location main memory. Essentially, we're gonna do processing using DRAM in main memory. And we're gonna see a bunch of works. This is an incomplete list of works that we're gonna cover. But basically, this is a summary. Essentially, I'm gonna show you how existing DRAM chips, or how, based on circuit theory, we can support bulk bitwise operations in DRAM. Copying, initialization, zeroing, bulk bitwise and or not, majority, nor NAND operations. We're going to see how to generate true random numbers inside DRAM. And also, I'm going to not talk about it, but you can do physical unclonable functions. Maybe we'll do it when we talk about some other security issues in memory later. And you can do more complex computation using lookup tables like we discussed earlier, right? If you want to do multiplication, for example, you can have a lookup table for multiplication. And then you don't need to implement an expensive multiplier, right? Especially if your multiplication is low bit width. If it's 32 by 32 multiplication, then you may have trouble, right? That's 2 to the 64 entries in your lookup table, unless you can somehow compress it based on values that occur frequently. So you can actually exploit that sort of thing in lookup tables also. Yeah. Okay. Anyway, or you can maybe do multiple accesses to your lookup table with some additional logic. So it's good to think about lookup tables, I think, going into the future. So we're going to see a lot of these mechanisms can be implemented low cost. It's not going to be no cost. It's going to be low cost, hopefully. Some of them are high cost. And we're going to see how to do this, all of these, using analog computation capability of DRAM. And essentially, the ideas are going to be relatively simple. We're going to see how activating multiple rows, either sequentially or concurrently, performs computation or data movement. Actually, if you activate multiple rows sequentially, you get data movement. You move one row to another row, essentially, the values of one row to another row. And if you activate multiple rows concurrently, you enable computation. And we're going to see why that's the case, based on circuit theory, as well as, fascinatingly, even in commodity off-the-shelf DRAM chips that are not designed for this purpose. So we're going to use the infrastructure that we discussed yesterday on testing DRAM chips, violate some timing parameters, and show that you can actually see essentially all of these functions. Does that sound good? That's the fascinating part to me, basically. Okay. And we're going to see significant performance improvements if you actually take advantage of this. Of course, a lot of this needs to be in simulation. Although, based on our results in commodity off-the-shelf DRAM chips in 2024, there are some recent works in the field, maybe we'll have some discussions on that later on, that show that you can actually do matrix multiplication or LLM acceleration in DRAM, low bit width LLM acceleration, even using existing DRAM chips. So there's an interesting area that started based on that. Okay. So to get to this, let's go over what's happening inside a DRAM chip first. So a little bit background. If you actually have taken DDCA, this is going to be background to you. But still, I think a lot of you may not have taken DDCA. So that's a DRAM module today. A DDR module looks like that. Inside the DDR module, you have a bunch of chips. Again, I'm not going to go through why you have this module structure that's part of DDCA. It's not important at this point. But inside the DRAM chip, you have something that looks like this. And the design of DRAM has many goals. The main goal is cost and density, basically. But robustness is important. And there are other goals also, as you can see. And we've discussed some of these goals earlier. But if you look at the DRAM chip, essentially, there are 8 banks. And each bank has a structure that kind of looks like this. This is cartoon, of course. It's not exact based on this chip, but this is cartoon. And I'm going to explain things using this cartoon. The actual number of banks is actually, 8 is actually the right number, but the actual number of subarrays is usually 128, maybe 256 inside a bank. Okay, so to sense the data inside a cell, you need some structure called a sense amplifier. And this is a very rough, let's say, approximation of what a sense amplifier looks like. It's essentially an SRAM circuit, right? SRAM stores data this way using 2 cross-coupled inverters. You've seen that. And you need to basically put the data in, and that's going to come from the top. And we're going to sense this, and the bottom will be the inverse of the top. So this is the inverter. That's how you're going to capture data. So this is a data capture device also, if you think about it. It's a sense amplifier. There's an enable signal that enables the sense amplifier. There's some additional circuitry that enables to amplify the data that it senses. As we're not going to go into the analog parts of the sense amplifier that much. It's not part of this lecture, but it works. People design these things in DRAM, and we're going to see how it's done in DRAM. So if you enable sense amplifier to be 1, and if the top of the bit line is VDD, if the top of the sense amplifier is connected to VDD and the bottom is connected to 0, this is called logical 1, let's say. That's our encoding. And if the top is 0 and the bottom is VDD, highest voltage level, then this is called logical 0. These are 2, let's say, stable states of the sense amplifier when it's enabled. Either it could have sensed either a logical 1 or logical 0. Okay, this makes sense, hopefully. You don't want a 0 on top and 0 on the bottom because that makes no sense logically, right? If you do that, then you're in a metastable state, and eventually the sense amplifier will come to something, but we don't know what that will be. If you took DDCA, you know what metastable states are, but we're not going to go into that detail at this point. Okay, so basically, how does sense amplifier work? You have a top voltage, VT, and you have a bottom voltage, VB, and top voltage, assume that top voltage is greater than bottom voltage. And you enable the sense amplifier. What the sense amplifier does is it senses that difference and it amplifies the top to VDD, bottom to 0. Okay, that's an amplification loop. That's what the cross-coupled inverter helps, but enabling is necessary. So initially, if the sense amplifier is not enabled, the top and bottom can be both some same voltage, and usually we put it into reference voltage, 1 half VDD, half VDD, half VDD, but the sense amplifier is not enabled, meaning these cross-coupled inverters are not connected to each other. As a result, you're in a reference voltage, VDD over 2, okay? But if top becomes larger than bottom, we will see a mechanism for how that will happen. And the sense amplifier gets enabled, then this cross-coupled inverter will amplify the top to VDD, highest voltage, and bottom to 0. Okay? Hopefully these all make sense, right? Based on logical circuit principles. Okay, now let's take a look at the capacitor. We're going to connect the capacitor to the sense amplifier later. This is the capacitor. Again, it's different from the physical capacitor, but logically we represent it this way. There's an empty state where the charge is logical 0. There's a fully charged state where it's logical 1. And unfortunately, capacitor directly itself cannot drive large circuits. It needs to be sensed carefully because it's very small, and we want to make it even smaller, as we know, and that causes us the scaling problems that we discussed last time. And reading the capacitor destroys the state. So if you read the charge and you, let's say, sensed it, its state is destroyed, right? Because you took out the charge from there. Okay. So we connect the capacitor to the sense amplifier so that we can sense things, right? For example, if the capacitor discharged, when we connect to the sense amplifier, we should be able to read a 0 at the top of the sense amplifier. If the capacitor is charged, when we connect to the sense amplifier, we should be able to read a VDD, essentially 1, when we sense it using the sense amplifier. Okay, we're going to see how that works. And this is how it works, basically. This is one DRAM cell connected to a single sense amplifier. This is the capacitor. Let's assume it's charged. Discharge is similar, but we're going to look at the charged part. And then there's an access transistor, which also we have seen earlier. It's turned off right now, meaning capacitor is not connected to the bit line over here. We're going to call this bit line. And there's a word line that connects, that controls the access transistor, which is not shown over here. And this is the cross-coupled inverter, sense amplifier. Initially, it's not enabled. And initially, this circuit is in pre-charged state, meaning both ends of the sense amplifier are equal voltage, which is equal to the reference voltage, 1.5 VDD. Okay? So this is our stable pre-charged state where the capacitor is not connected and the bit line, both ends of the sense amplifier are charged to the reference voltage. Now, if you connect the access transistor, meaning enable the access transistor by enabling the word line, which we will also see later, you connect the capacitor to the bit line. And because the capacitor is fully charged, what it does, it loses some charge through that RC path. And it basically perturbs the bit line just a little bit. It has a small amount of charge, so the charge perturbation is relatively small. And at some point, sense amplifier gets enabled because, so this happens when you do an activation command. You activate, and activation enables that word line to connect the access transistor or enable the access transistor. And after some point, some charge gets propagated or shared with the bit line, and the bit line charge gets perturbed. And after some point, some circuitry enables the sense amplifier so that that perturbation is amplified. That's the sense amplification to VDD on top and 0 at the bottom. This is how you actually get sense. And then what happens is because the sense amplifier is very, very strong, it amplifies the voltage over here to VDD, and it keeps amplifying it. It's a basically feedback loop, as you can see. And essentially, it restores the charge of the capacitor to VDD because it's really pushing back electrons inside the capacitor over there. Make sense? So basically, this reading process, activation process, when you activate a cell by connecting the access transistor to the, basically by enabling the access transistor, you share the charge with the bit line in the capacitor, and then sense amplifier gets enabled to amplify the charge, and then the charge gets restored back into the cell. So even though you destroy the state of the cell, you put it back after the restoration process. So that's how a single cell in DRAM operates. And you may have seen this in DDCA, but I think it's good to see it again because we're going to build on it. And in DDCA, we built a bigger array out of this. So let's take a look at the single cell. And now I'm showing you a full bit line. Oh, what happens? Yeah. I'm showing you a full bit line. We basically build a subarray on top of it. In a single bit line, you can actually hang off multiple of these cells. So this is, well, what's happening? Okay. You can see that this is one DRAM cell, another DRAM cell, another DRAM cell. These are different rows, 3 different rows. Another DRAM cell, another DRAM cell. So this subarray has 6 rows. 3 of them are on this end of the sense amplifier, 3 of them are on this end of the sense amplifier. This is one design of a subarray. There could be multiple different designs, which we're not going to get into right now, but when we talk about latency, we may get into some more. And this is one-dimensional, clearly. And this reduces the cost right now, right? Because a sense amplifier is actually a pretty expensive circuitry, right? It's 2 cross-coupled inverters, at least 4 transistors right now. And it needs to be big so that it can sense things in a good way, in a reliable way. So the size of the sense amplifier is actually much larger than what is depicted over here. This is not to scale, if you will. So in order to amortize the cost of the sense amplifier, what people do is they actually add a lot of cells on the bit line, 512 or 1024. That amplifies the cost of the sense amplifier, but also that increases the latency right now to sense, because now you have to go through the bit line when you share the charge. And we're going to see this fundamentally when we talk about memory latency. Now, there's also, in order to amplify the cost of the decoding logic, what happens is when you enable a word line, you don't enable a single cell, but you enable a multitude of cells. You can see that this word line over here, okay, that's a bit annoying. Maybe I should get this to me also, but I'm not going to touch that because who knows what happens when I touch it. So you can see that this word line here is connected to 1, 2, 3, 4 cells. So basically, when you activate that word line, you're really sensing 4 cells concurrently in 4 different sense amplifiers. That's a row, basically. Here you see a row in 4 cells. A row consists of 4 cells. And the reason is to amortize the cost of the decoding circuitry that's not shown over here, right? Because you get an address, you need to determine which row the cell that you're going to read is on, for that you need a decoder. Right? And that decoder, if you actually have a row whose size is only one cell, you need to have many, many of those decoders. Right? That's the problem. Now, actually, we amortize the cost of that decoder across all of the cells in a row. And in this particular case, you see 4, but in real DRAM, it could be 2 kilobytes, 4 kilobytes, 8 kilobytes. So many cells that get activated concurrently. And this is a subarray. This is not this just piece of the DRAM. And that's the enable circuitry for the sense amplifier, which needs to be there. So there's a row decoder now. You can see that when you're given a row address, that row decoder figures out which row you're accessing and enables that. And this is the array of sense amplifiers, which is also called row buffer. In this particular case, we have 8 kilobits of them in a subarray, which is not an unreasonable number. It's actually a common number. And these two cell arrays together are the same subarray. Make sense? Okay, this is one design. There could be multiple different types of designs, but the fundamental principle is the same. Okay, so now how do you build bigger DRAM banks? You essentially replicate the structure. You have, in the top, you have one subarray. In the bottom, you have another subarray. That's the idea. In real DRAM, you have 128, maybe 256 subarrays, maybe more subarrays in a single bank. Of course, the number of subarrays affects your row decoder, global row decoder also. There needs to be another row decoder over there to decide which subarray you're accessing, right? That's not shown over here yet. There's a global decoder. And also, when you access a particular row, you read the entire row into the sense amplifiers, right? Because you activate all of the cells. If you go back over here, let's go back. We're going to see this again, but you activate all of the cells in this row, and all of them concurrently perturb their sense amplifiers in the bit line, and all of them are read concurrently in the sense amplifier, right? So that's the activation we're going to see. And then you need to get the data out of the chip, right? Because sense amplification just takes the data and puts it into the sense amplifiers activation. How do you get the data out? You need to send a read command to DRAM, which brings the data from a piece of the sense amplifiers, piece of the array of sense amplifiers, piece of the row buffer. It's called bank IO, routes it outside the chip. So this is a huge interconnect, much bigger interconnect, because if you think about the sensing from the cell array inside the subarray to the sense amplifier, that's a shorter interconnect, but a lot of wires, shorter but high bandwidth. To get the data out of the DRAM chip, normally you don't have 8 kilobits of wires. You actually pick, let's say, 64 bits, sometimes even smaller. You basically pick 64 bits of those 8 kilobits, and you have corresponding interconnects that route the data across the entire bank. Now, these interconnects need to be much bigger because they are covering a much larger distance. And those interconnects are also less efficient. Because they need to be much bigger, you cannot have 8 kilobits of them also, because they're expensive. And as a result, even though you may read the entire array of sense amplifier, you may actually get the data into an entire array of sense amplifier. You actually activate an entire row. You get only a piece of it with every read command from DRAM. Okay, so there are a lot of reasons for design decisions, right? Okay, and then the address comes from somewhere. So both of these involve addresses. One of them involves the address of the subarray plus the address of the row to activate the row. And the bottom over here, you need an address also to decide which part of the row buffer you're going to read. That's called a column in DRAM. Okay. Okay, so let's take a look at a little bit differently. So a memory channel can be 8 bits, 16 bits, 32 bits. So this is the DRAM chip's output. It can give you 8 bits only. And this is important because this actually determines your cost. So how do you get those 8 bits? So you have all of these banks, and each bank has multiple subarrays. So they share this internal bus. And that internal bus gets loaded with 8 bits at a time. Okay? Well, now what might happen is you may actually fetch 64-bit of data into some bank IO circuitry, and then you get the 8 bits afterwards. So internally, there could be different design decisions. They're not that important right now, at least. But let's take a look at the operation of this. I already given you the operation, but let's assume that this is your bank. You first need to, let's assume that you want that piece of data, the black piece of data. I don't know why this, okay. I know why it's not working, but let's assume that you want this black piece of data. First, you need to activate the row that has that data. So a memory controller sends the address of the row to the DRAM chip, saying activate this row in this bank. So the memory controller needs to know which bank and which row, of course, and that gets sent. And the DRAM chip decodes the row address and activates the row, which enables the word line. So row address gets sent, and then sensing happens across all of the bit lines of this row, and then also restoration of the charge happens. And now you have this part that you want to read inside that row buffer or array of sense amplifiers. The next step is to read that part essentially. Use the memory controller sends a read-write column address to that same bank to the DRAM chip, and this comes as a column address. And the DRAM chip, using those long interconnects that span the entire bank, there's some also additional circuitry that we didn't show. It's essentially a multiplexer. You multiplex the right column out of that 8 kilobits of data, and then you send it through the bank I/O and send it through the data pins of the DRAM chip. Okay, if it's 8 bits, you send 8 bits, but you may fetch 64 bits and then you send 8 bit at a time, right? So there's some internal prefetching that happens in DRAM as well. Okay, so that's reading, writing. Well, this is reading actually, not writing. Writing puts the data in the opposite direction. And in fact, there's additional circuitry that's to enable writing. And then if you're done with that data, if you want to open another row, for example, you pre-charge the array. The memory controller sends a pre-charge command to the DRAM chip to that bank, because pre-charge happens at the bank granularity. And the memory, when the DRAM chip receives a pre-charge command for that bank, what it does is basically there's some pre-charge circuitry, which we also didn't show completely. But what it does is the goal of the circuitry is to close the row that's active in the sense amplifiers, which requires you to reset the sense amplifier to the stable pre-charge state where both ends of the sense amplifier are VDD over 2, reference voltage again. So the additional circuitry is needed for that purpose. Makes sense, hopefully, right? This is actually how modern DRAM operates. Now you have hopefully a very good idea of how modern DRAM operates. There are, of course, some other things that to know, but they're not necessary right now. Any questions? Okay, yes, you go first. Yes. Yes, absolutely. Yeah, they're absolutely. They're wider, they're thicker. There's a lot of signal integrity concerns internally to design these things. And DRAM manufacturers are very, very good at that. Because one of the other issues with DRAM processes, they need to be thicker. As a result, you cannot have many of them. And also, you don't have a lot of metal layers to add interconnects because of the fabrication process. It's not as good as logic process today. As a result, you need to be very careful in the design of these things. Yes, you have a gun for questions? Gun. I cannot hear you. Can you speak up? Uh-huh. Uh-huh. Mm-hmm. Yeah. Mm-hmm. Yeah. Mm-hmm. Yeah. That's a good question, but I'm not going to answer you because that's a good research question. You can discuss it. But I agree, yeah, this is designed, this design is there because it's designed as memory, right? The goal is to maximize capacity. Essentially, that's the only goal of this design, I would say. It's not even to minimize latency. We're going to see the latency later on. But there are some latency concerns, but yeah, that's one of the major reasons. The question is, it's a very good question. I'm going to pose it back to you guys later after this lecture. Hopefully, you'll be more equipped to think about that question. And that's a really good research question. Basically, if I were designing this as a compute engine, in addition to memory, I'm not going to get rid of memory completely because there's a huge benefit of having large memories. How would I design this architecture? Right? That's a great research question. That's a great PhD thesis. Rahul was my 25th PhD student, and maybe you can be 35th. I'm just kidding. Because there's a pipeline after Rahul. It's a deep pipeline. Yeah. But basically, that's a very good PhD. That's why I don't have the answer, basically. We don't know. And no one has done this. No one was bold enough to do this, right? We're doing this right now, essentially. And this is a good time to do this. The question you ask is a great research question to research right now. Make sense? Okay. Maybe you'll have some ideas and we can discuss. Okay. 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 So this, if you're interested in background on in DRAM operation with my PhD student Vivek, whose work I'm going to describe soon, actually, we have written this long chapter that talks about how DRAM operates, and I think this is a very clean way of describing how DRAM operates. And I borrowed some slides actually based on that. Okay. Okay. So now let's, with that background, let's go into how you can do computation inside DRAM. And I'm going to cheat. I'm not going to even do computation first. We're going to do data copy initialization, which is also very important, actually. So we do a lot of data copy initialization on our workload. So, for example, when you deallocate some page, the operating system, a good operating system, I should say, clears that page. Either zeros it or randomizes it, so that the contents of the page is not available to anyone. Because that page, that physical page, can get recycled. Some other process may have access to it, and someone may actually read your data if they get access to it, right? So a good operating system clears that page in some way, randomize the data. Most operating systems do that. In fact, they have a zero-page pool in general. When you deallocate the page doesn't get zeroed immediately. It goes into the pool to be zeroed, and then eventually it gets zeroed by the hardware, and then it becomes available for use for other processes. That's zero initialization, for example. Forking, when you fork something, you copy the data of the thread that forks, let's say, child thread, right? When you clone a virtual machine, you copy a lot of data, actually. When you migrate one page from one place to another place, you copy a lot of data. Basically, there's a lot of copying of data that happens both at the application level as well as the system level. And can we do this better? Basically, that's the question. And in this paper that I mentioned about from Google, from ISCA 2015, if you remember, where they showed most of the time the processor is waiting for data, and only 10 to 20% of the time it's finishing instructions. They also have a more detailed analysis of where the time is spent in the data center. And they say only these two function calls, memmove and memcopy, occupy 5% of the execution cycles across the entire data center, across all of the workloads. That's a bit fascinating because two function calls, right? There's not all of the data moments, but just two function calls are responsible for 5% of the execution cycles. And later in that paper, they say, if you, like the approaches like what I'm going to describe next, RowClone, because our paper was published earlier than their paper, are going to be much more important into the future to overcome this sort of data movement bottleneck because of data copy. And also, I should say, initialization is a special case of copy, right? You may say initialization, you're initializing something with zeros. You can do it without copying, potentially, but you can do it with copying also. You initialize something with zeros and then you copy that zero everywhere, right? That's initialization. It's good to think about it that way. Okay, so how do we do bulk data copy today? We're going to look at bulk data copy to begin with, meaning large data copy. Let's assume that you have this white page and then you have this gray page. How do you do copying today? Basically, we go through the processor because we cannot do it anywhere else. Well, we can do it in the memory controller. So we can do it near memory a little bit, but let's go through the processor right now. You bring the source page, let's say 4 kilobytes, byte by byte, into the L1 cache, in fact, into the register file. And then you bring the destination page, byte by byte, into the L1 cache and the register file. You do the copy or write of the source page to the destination page, move essentially. And then you write the destination page byte by byte back into the memory. So that's 12 kilobytes of data moved. And it disturbs a lot of things. Basically, it's high latency because you're accessing memory a lot. It's high bandwidth utilization on perhaps the biggest bottleneck that we have in our systems, which is the memory bus today. And it causes cache pollution in the caches, especially if you're not going to reuse the destination page anytime soon or the source page anytime soon. But you could eliminate that cache pollution part by doing this through the direct memory access engine in the memory controller. So there's a way to not pollute the caches and do this copy inside the memory controller through direct memory access mechanisms. But I'm not going to talk about that. That reduces things a little bit, but still not good enough. And that causes a lot of unwanted data movement, because if you don't reuse the data, imagine like you initialize a 1 terabyte database, right? Your entire memory, let's say, almost. You basically go through the entire terabytes. There's no reuse that you have over there. Okay, so today, if you actually do a 4 kilobyte page copy via the direct memory access engine without going through the memory hierarchy on the CPU, it's about 1,000 nanoseconds and 3.6 microjoules in memory. Okay, so it's good to think about this. In the last lecture, I said sometimes maybe we should be thinking like a 10-year-old, right? And you give this picture to a 10-year-old kid and you respect them. You don't be a bad tram driver. You respect the 10-year-old kid and say, okay, I'm doing this. What do you think? It's always good to ask the question, like, what do you think? Don't lead them. They will basically say, why not just do this, right? Because these things, maybe you can give them even more context. More context is basically the source and destination are very close to each other in memory, right? They could be in the same subarray, actually. Or I could put them in the same subarray. What do you think? And they will probably come up with the solution, right? Basically, as I said, we should be like 10-year-old kids, because maybe they don't have this baggage to make decisions. They certainly don't have any self-interest or bank accounts to fill yet. So basically, if you do that, they will come up with the solution. And that's what we're going to do, basically. And this is going to be low latency, low bandwidth, no cache pollution, and no unwanted data. So I'm going to show you a mechanism that takes that 1,000 nanoseconds for a 4 kilobyte page copy to 90 nanoseconds unoptimized. You can optimize it more, and takes the 3.6 microjoule energy spent on that operation to 0.04 microjoules. Again, that could also be optimized more. And the basic idea is very simple. Now you know how DRAM operates, right? I'm going to show you the high-level idea first, and then we're going to look at the operation also internally in DRAM. This is the DRAM subarray that I showed you earlier with some more cells. And then there's a row buffer, sense amplifiers. I put it at the bottom. It could be in the middle. Doesn't matter. Let's put it at the bottom for now. Basically, what we're going to do is we activate the source row first, which brings the data into the sense amplifiers. Right? This is activation, and we've seen this. Now, in the next step, I'm going to activate destination row, which implicitly will activate the source row and connect the sense amplifiers to the destination row. That's the idea. By doing 2 consecutive activates, we can first activate the source row, which will bring the data into the sense amplifiers, and then next activate the destination row, which will bring the data from the sense amplifiers to the destination row. We use the sense amplifiers or row buffer as a temporary buffer to store the contents of the source row, essentially. That's the idea, and this is negligible hardware cost in the original paper. And this is really based on the chart sharing properties of DRAM. So let's take a look at this. This is inside the same subarray. So this is basically, I'm looking at source and destination. And this is the initial pre-charge state. Let's take a look at the activation or the source row. I activate the source row. Source row has a charge state, which shares, the sense amplifier perturbs the bit line. And then sense amplifier gets enabled, amplifies the difference. And you can see that that becomes VDD. And at some point, it gets restored. You don't need to wait until that, actually. But let's assume that you waited. This is the actual activation operation, right? And then if you activate the destination row while deactivating the source row, this is what happens. Now, the destination, in this particular case, 0, it's the sense amplifier is very strong, as you can see. It's actually driving VDD. It already drove VDD into the source. It will drive VDD into the destination also, right? Because it's restoring the charge. Basically, it's doing the same thing it did to the source into the destination. Make sense? That's the idea, basically. That's the idea of the copy. We use the existing circuitry. We didn't add any other circuitry here, as you can see. Yes? That's correct, yes. So because you're now filling more than just the source, there's some additional power you spent. But compared to bringing all of this data into the CPU and doing the copy in the CPU and then writing the data back, much little power. But compared to a single activation, yes, there's excess power. Okay. Any other questions? So basically, this improves latency by more than 10x. The latency of a 4 kilobyte page copy, and energy, memory energy, this more than 70x, which is good. So this is the RowClone paper. This is going to be one of the readings that you can choose. I'm not sure if it's a required reading yet. It's fun. It's a fun paper. It was rejected the first time it was submitted to ISCA. So I have a lot of these stories about paper rejections. People don't think this is an important problem, but anyway, it's interesting to think. So later, some folks built on this work. This is from Princeton. They used the infrastructure, the soft MC infrastructure that I showed in yesterday's and also previous days lectures. And they basically said, oh, what happens if you violate the DRAM timing parameters? And they basically showed that if you violate the activate to activate timing parameter, you can actually see the RowClone operation on real DRAM chips. They call this compute DRAM. Okay, we're going to get back to that. We built on their work, and we introduced this PyDRAM infrastructure, which is essentially an end-to-end infrastructure where we violate the DRAM timing parameters to perform RowClone. We also violate the DRAM timing parameters, read timing parameters, or activate timing parameters when you're reading, to do true random number generation. I'm going to explain that later. But this is actually a very interesting infrastructure. I think there needs to be more infrastructure to be built in this area for DDR4, DDR5. But what this infrastructure is doing is you have, on the FPGA, you have a RISC-V processor, a very wimpy one. You could change it to, if people are interested, you could use the Jiangshan processor from China and make it much better, maybe. But essentially, that RISC-V processor is what's executing our program. We change the operating system such that when you do a copy, the destination page is allocated in the same subarray as the source page, because we want to be able to do this. And when you get a page copy operation, when the destination page is in the same subarray as the source page, the processor ships that page copy operation to the memory controller, which we modified ourselves. And the memory controller violates the timing parameters, activate timing parameter, and performs the page copy inside the DRAM without any modification to the existing DRAM chips or the interface. And when it knows that that's done, based on the timing, etc., it basically notifies the processor saying that I'm done with the copy. You can move on. So that's the idea, basically. It's an end-to-end system that can perform this page copy inside the DRAM. You can test applications with it. You can test micro benchmarks. It also does random. So whenever you have a random function call, rand function call, for example, it gets shipped to the memory controller also. And the memory controller generates the random numbers, as we will describe later. And you can do that. So this is fascinating. You can build full systems, as you can see, that can do page copy, that can do random number generation inside DRAM without requiring any modification to the DRAM chip or the interface. You just violate the timing parameter such that the activation to the first row and the next and the destination row in the same subarray happens quickly so that you can do the copy internally. That's the idea. And if you're interested in this sort of prototyping, there's a lot of potential for this thing. This is DDR3 right now, but this is an example, as you can see. This is real results for real copy micro benchmarks. And you can see that the initialization micro benchmark and copying micro benchmark, you get significant improvements in throughput. And one of the reasons for the huge throughput improvements, copy throughput or initialization throughput, is because the RISC-V processor is very wimpy, 50 megahertz or so. If it's much better, maybe that number is lower, but still significant. Okay, that's PyDRAM if you're interested. There's a lot of opportunity here to build more infrastructure. Okay, so that was copy inside the same subarray. What if you want to copy things that are a little bit farther away? And what if you want to copy things that are not at the page granularity? So a page copy is a special primitive that's used in forking, for example, and that's used in when you initialize huge amounts of things like pages, multiple pages, many pages. But what if you want to copy one byte to another byte, right? That is also supported, although it cannot be supported in existing DRAM chips while violating the timing parameters. No one has discovered that yet. If you discover that, that'd be a big discovery, in my opinion. In my opinion, very tough. But basically, there's a shared internal bus that I showed you earlier, right? 8 bits. Yes. Well, You need to copy the entire row in existing DRAM architectures because you activate the entire row. Yeah, you need to change the DRAM architecture to copy partially within the subarray. Yeah, but across different banks, you can copy any piece. Yeah, of the row. Yes. Mm. Yeah. Potentially. Not with what I just described, but you need to add additional circuitry again. Yeah, it's possible to do it, but you need to add additional circuitry. And these are very good ideas, basically. How do you transpose data? We proposed solutions to that for other reasons, but not necessarily inside the DRAM. But you can also potentially put it inside the DRAM in the logic layer, for example. It's good to think about that. Yes. Now you're thinking if the memory is more of a compute unit or data reorganization unit, how would you design it, right? Good thinking. Okay, let me give you this idea. We're going to take a break soon, but basically, there's a shared internal bus. And let's say you want to copy these 3 bytes, 8 bits, the green ones, from that bank to this bank. They happen to be there. Right? With page copy, you have some freedom, actually, if you think about it. Or page initialization, you have a lot of freedom. With page copy, initialization happens to the page, so it's a lot of freedom. But page copy, you can allocate, especially if you're doing it at the page level, you can allocate the destination page in the same subarray. Right? So the operating system, you can modify the operating system. But if you're doing small scale copies like this, they may be anywhere. But you can set the source bank to the read mode and the destination bank to the write mode and pipeline the reads and writes. This is possible, but it's not supported in existing DRAM chips. Almost all of the infrastructure, essentially all of the infrastructure is there in the DRAM chip. Normally, when you read the data, for example, from here, it goes out to the memory channel. Instead of going out, you just basically take it in. And then normally when you write the data to the DRAM chip, it comes from the memory channel to here. You just need to get it from there, right? So essentially all the circuitry is there, except the DRAM is not capable of being used in this way. Okay, so we show in the paper that you can get significant latency and energy reduction for this sort of copy as well. This could be improved also with some changes to the DRAM microarchitecture. So there are many other questions after this. In the paper also covers like initialization in detail, and also what about inter-subarray copy, which is very tough to do in that paper. So we're going to look at some questions. Can this be improved to do faster inter-subarray copy? Can we enable data movement at smaller granularities within a bank? And we have some mechanisms, but I'm not going to talk about all of these details. Can this be implemented to do better inter-bank copy, for example? If you have 3D stack memory with a nice logic layer, you can have better interconnects across the banks. So basically, we're going to add more and more connectivity inside the DRAM chip. That's one of the problems with existing DRAM chips. There's not enough connectivity across the memories. The goal is to, again, get the data out, right? The goal is not to reorganize the data. The goal is not to compute here and then compute there and then merge the data. So the connectivity inside the DRAM chip is very low today. And then we're going to talk about can similar ideas and DRAM properties be used to perform computation? Because I kind of cheated, as I said. I showed you data copy and initialization. But I think this is a good time to take a break. Let's take a break until 2:45. And then we're going to start with this. And let's see where we'll go until. Okay. Is it good? Can you hear? Okay. Okay, wonderful. So we can get started. So remember, oh, that's not working. Let's go back. Okay. Remember, we covered RowClone, which is, I think, a nice idea, but it does require changes to the stack, meaning your ISA needs to be able to specify page copy operations to the processor, which is actually done in a lot of the ISAs today. In the RowClone paper, we discussed, for example, Intel, x86, and also PowerPC ISAs. They both have page copy instructions, and also small scale copy instructions as well. Your operating system needs to be allocate pages nicely so that you can maximize the page copy that happens inside the same subarray. That's important. And also your processor needs to be able to ship the operations to the memory controller so that the memory controller can execute them. That's going to be true for essentially everything that we're going to discuss forward, because you need to be able to specify these operations, processor should be able to ship them, and operating system should be able to allocate the pages that you operate on in the right places in memory. So processing in memory requires changes across the stack, but some of the changes may need to be small, depending on whether or not those operations are already expressed in the ISA. So it's good to think about that. But we're going to cover some more of these later on when we discuss adoption issues, programming issues that affect the entire system. Right now, we're kind of building the base of how can we do data movement, not even computation to begin with, right? Okay, so right now we're going to cover a little bit more. So this is an interesting idea that has multiple benefits, and I call it increasing connectivity in DRAM, which is something that I suggest is important to do. RowClone doesn't change the connectivity that much, and as a result, it suffers from some things. So we call this LISA, low-cost interlink subarrays. So basically, DRAM kind of looks like this. Inside a bank, you have two-dimensional array of cells, and they belong to different subarrays, basically. And you can see that one subarray may have 512 rows and 8 kilobits of columns. Internally, when you want to get data out of a subarray, there's an internal data bus, as we have seen, which is 64 bits, that takes the data out to the bank IO, what is called, and then drives it outside the DRAM chip. Now, if you want to copy data from one subarray to another subarray, you cannot do it at large granularity, right? You're limited to fundamentally the 64 bits. That's why RowClone is not possible, or at least intra-subarray RowClone is two activations, right? You activate one row, and then you activate the destination row, and that happens through the sense amplifier. But if you want to copy data in subarray 1 to, let's say, subarray 2, there's no connectivity other than this internal data bus, 64 bits. Basically, the question is, can we somehow extend this connectivity to enable more freedom to copy data inside DRAM? And the idea is, yes, but you need to change the DRAM. Essentially, we're not going to shy away from changing DRAM in this course or changing memory. And the idea is to add more connectivity, provide a new substrate to enable wide connectivity between subarrays. And this is one example connectivity. I think we should be adding more connectivity. And I think if you look at a processor chip today, there's a lot of connectivity across cores, etc. But if you look at a memory chip, there's very little connectivity across even subarrays that are just next to each other. Right? So it's a bit fascinating. And this is the mindset, as we have discussed earlier, because of the way processors have evolved, adding interconnects easy. Because of the way memory has evolved, it's just a memory, right? You don't do computation. You don't want to even do data movement inside. So you don't need that connectivity. But if you want to do data movement inside, if you want to do computation inside, you should think about more and more connectivity inside the memory chip. Okay, so the key idea, I'm going to give you the key idea. Essentially, we call it low-cost interlink subarrays, but we want to enable fast block data movement between subarrays. And to enable this, you need to have a way of connecting the bit lines in one subarray to the bit lines in another subarray. That's it, basically. Today, they're not connected, and we're going to add isolation transistors to enable that connectivity. Isolation transistor is a special transistor that can enable or disable. If you enable it, things are connected, like a wire. If you disable it, things are disconnected, basically. It's very simple. So this is the idea. You have one subarray, another subarray. You've seen what they look like. We're going to add these isolation transistors, and we're going to enable or disable them. If you enable them, the top bit line in that top subarray gets connected to the bit line in the bottom subarray, so that you can get the data from that bit line and put it in the row buffer of the second subarray. Makes sense, hopefully, right? It's essentially a longer bit line now. You can think of it that way. Okay? That's the idea. Hopefully that's clear. I'm not going to go into a whole lot more detail over here, but that's it. It's a very simple idea, but no one has done it, which is fascinating. And I think that's a very cool idea. I think people should be thinking more and more about this sort of connectivity. Now, what does this enable? This enables basically a faster bulk data copy across subarrays. So you cannot do this with existing RowClone. What we did in the RowClone paper was we need to cover all the bases in the paper, right? What if the data source and destination are in the same subarray? That's fast, as I showed you earlier. What if the data source and destination are in different banks? I already showed you also. It's a bit slower, but there's a path. What if the source and destination are in the same bank, but different subarrays? Now, that's the hardest part. Basically, what we did in that paper was we copied the data from subarray 1 in this bank to some other bank first, and then from that bank to subarray 2, because we don't have that connectivity. So this is the connectivity that we add. So this way, you can actually reduce the copy latency between two subarrays from 1.3 milliseconds to 0.15, which is very close to the baseline RowClone copy latency, which is good. So you get significant speed up and DRAM energy on some workload that I'm not going to discuss over here. The paper has a lot of details. You can also do other things, which we're going to cover in some other lectures. So this is going to be interesting. This is something that I'm not going to spend a lot of time right now on. But for example, what you can do is you can have one subarray that's large, another subarray that's small. And small subarray can be a cache for the large subarray inside the DRAM. What's a large subarray? Large subarray has very long bit lines. Long bit lines are longer latency to access. Small subarray has short bit lines. It has shorter latency access. So it can act as a fast cache compared to a large subarray. And this way you can do caching inside the DRAM, which is something that people don't do today. And that actually leads to speed ups. You can reduce the hot data access latency significantly. And you can do something else, again, which I'm not going to talk about right now. We're going to talk about these, especially the caching and pre-charge and the latency lectures, because they're more related to latency as opposed to computation inside DRAM. So if you have this sort of connectivity, what you can do is you can have faster pre-charge, because you have a pre-charge circuitry in subarray 1 that pre-charges subarray 1, but you also have a pre-charge circuitry in subarray 2 that pre-charges subarray 2. Now, if you want to pre-charge subarray 1, you can also use the pre-charge circuitry in subarray 2. So you can use two pre-charge circuitries at the same time to drive more charge so that you can pre-charge the same subarray. And the reason you can do that is because you now connected the bit lines of the two subarrays to each other with isolation transistors in a configurable manner. That's the idea. So you can actually reduce the pre-charge latency significantly from 13 nanoseconds to 5 nanoseconds according to our circuit simulations. So you can see that this sort of idea is not just good for moving data, but also it has other benefits. Yes? How many subarrays do you need? Excellent, yeah. I'll refer you to the paper, basically. But yes, in the paper, I think we move at most 2 subarrays and then lash the data inside the sense amplifiers. And then if you want to move further, you can do another. We introduce a row buffer movement, what we call the row buffer movement operation. So you need to send more row buffer movement commands if you want to move from subarray 1 to subarray 256. And what you're limited by over there is the distance, right? If you actually want to move from subarray 1 to subarray 256, let's say, assuming those are the most distant subarrays, then you need to traverse a very long interconnect. And there are 2 issues over there. One is latency is long. The other is you may not have the signal integrity, because these are not essentially, you have a very long, thin bit line, and you may not be able to reliably transmit everything, even if you wait forever. You see what I mean? Because it's not designed, at least currently, for that purpose. So we limit ourselves to 3, but probably you can do more. We have a sensitivity study in the paper that shows what happens. What happens to latency if you go up to 16 or 32? I don't remember the exact number. Say it again. Yeah, you can go from 1 to 3, basically. Yes, yes. Yeah. But this now gives you more flexibility in terms of where you can allocate the destination page, for example. Yeah, there could be more studies over here. Maybe enabling movement across 5 or 6 is okay too. Yeah, but you'll get more longer latency for sure. Okay, any other questions? That's a very good question. Okay, moving on then. So that was Lisa in one slide. There's a lot more that goes into a paper, of course, than one slide, but you got the key idea. That's what matters, right? And now you know the trade-off also, hopefully. It comes at an expense, which is the cost of those isolation transistors, right? They're not necessarily cheap, even though we estimate it to be 0.8%. Maybe it's larger than that. We don't know. Probably it's larger than that, actually, because we don't have very good DRAM models to evaluate. And we cannot fabricate. It's too expensive. So we have to essentially see using modeling. Okay, but this sort of idea, I think, has a lot of advantages. It should be implemented. Okay, so some other things that I'm not going to talk about. This enables fine-grained relocation inside a bank. Again, from one subarray to another subarray, or from one subarray to the same subarray. If you want to move like 8 bits of data, how do you do it? Essentially, you move it to the peripheral circuitry in the bank. There are some latches over there, and then you move back into the subarray. And this actually enables caching benefits, for example, also data movement benefits. So it's similar benefits as Lisa, but you do it using the latches that are global to the bank. And then there is also more sophisticated things that you can do if you want to transfer data across different banks. And if you have a logic layer underneath the memory layers, then you can actually put a more sophisticated interconnect and route the data appropriately. And I think going forward, this adds more connectivity, of course, comes at higher cost. So it's very hard to do in a planar DRAM, but it's much easier to do if you have 3D stacking technology. And you can connect the banks in a much better way. And these are things that we should be thinking going forward. How do I increase connectivity in different types of DRAM? Okay, so you can see that the mindset is still a mindset of an accelerator, right? We're increasing acceleration capability. And there's more on RowClone and processing using DRAM. Probably this was one of the earlier lectures, right? No, this is a seminar meeting, apparently. Yeah, if you're interested in more detail, we go into more detail in that seminar course. Okay. That was data movement, data copy. We'll say more about that later on, but let's talk about computation. How do you do computation? So for data movement, data copy, we did 2 consecutive activations. We activated the source row and then we activated destination row, at least inside the same subarray. Actually, you do the same thing across the banks also, but you do other things as well, right? You activate the source row, you activate destination row across different banks, and then you pipeline the data movement. So it's still a consecutive row activation, but you do other things in between. So if you want to do computation, basically we're going to activate multiple rows. And this is described in this paper. But before I go into this, since we're not going to cover everything today, new memory technologies enable even more opportunities. New memory technologies are also capable of what we're going to describe in DRAM, but they actually do more, and they don't have destructive reads in general because they are non-volatile. So this is your familiar picture. Now I'm showing you 3 rows over here, A, B, C, 1 bit line, 1 bit in each row, 1 capacitor in each row, 1 access transistor in each row, and a sense amplifier. And the sense amplifier is disabled, as you can see, and it's a pre-charged array at this point. And 2 of the cells are charged and 2 of the cells are discharged. This was actually initially introduced in this 2015 paper. And it's the first paper that I know of in the DRAM space that looks at this sort of computation. If you find something else, let me know. There's papers in SRAM, but not in DRAM. So the basic idea is what happens if we concurrently enable these 3 rows at the same time. So if you do that concurrently in an ideal circuit, if at least 2 of these cells are charged, the top bit line will be perturbed to the positive state. And then these will get connected and the sense amplifier will get enabled and essentially amplify the voltage on the top part of the bit line to a VDD. And then restoration will happen. All of the cells will be restored to BDD. It's assuming that you have equal charge in all of them, right? That's not the real life, of course, but assume that that variation is under control in some way. Okay, so that was a bitwise majority function. What we just seen is bitwise majority. That's computation based. The chart sharing principles of activating 3 rows in an ideal circuit enables you to compute the bitwise majority of those 3 rows. In this case, 1 cell. But imagine that this is happening. You're computing the bulk bitwise computation of 8 kilobits of data by doing this 3-row activation. Makes sense, right? This is beautiful, I think. And this is a realization that, interestingly, no one has made until this work, which is also fascinating. That means that there's more to discover in this area, right? Or if they have not, if they have made this realization, they didn't document it, or it's in such an obscure place that we couldn't find it, let's say. Okay, so the good news is this is also bitwise majority is nice, but bitwise majority is composed of bitwise AND and bitwise OR. So if you set C to 1, you get the bitwise OR. If you set C to 0, you get the bitwise AND. That sounds good, right? Okay, now you can expose this to the ISA. Let's take a look at the interface. You can imagine an instruction that looks like this: bulk AND, A, B, C. And the idea is to perform a bitwise AND of 2 rows. Let's assume that rows are equivalent to pages. 2 pages, A and B, and stores the result in row C. And how do you do that? So we have an implementation in the paper. I will go through this relatively quickly. We'll go into implementation maybe more later. But essentially, it makes sense to have a reserved 0 row in one of the rows. It makes sense to have a reserved 1 row. Basically, row is reserved to be all zeros and all ones, 2 different rows. And then we have a separate part of the array that is there for triple row activation. So meaning there's a part of the array. Maybe I'll do this. How do we do this? Let's see. Okay. So do you know how to change this so that people can see what I write? Konstantina is the master. Okay, I don't know if you can see what I write, but I'll try while she's doing that. No. Okay. So this is your rows. It could be 512 rows. It could be smaller. Basically, we create another area over here. We call it the compute area. It's still DRAM rows, but here we have 3 rows. Actually, the paper shows more rows, but let's assume that it's 3 rows over here. These are D0, D1, D2. They're designated rows for triple row activation. This way, if you want to operate on some rows, let's say A, B, C, they're here, you need to move them here first. And we know how to move them now, right? RowClone. You do RowClone operations, RowClone A into D0, RowClone B into D1, RowClone C into D2. And then do a TRA on these rows, triple row activation. And then RowClone the result back to a destination row, which could be a D over here, right? Make sense? So for example, if you want to do OR of A and B, you set C to 1 first, which means if you have a reserved row 0, which could be here or there, let's assume it's here actually, reserved row 0, reserved row 0, and reserved row 1. If you want to do an OR operation, you move the reserved row 1, copy it to C first, RowClone from there to there. Okay? So with a few RowClone operations, 1 RowClone operation to move it from here to set C to 1. Actually, you don't need that if it's here, right? You don't need to move that again. So you can eliminate that. Basically, if you're doing just an OR operation and a not majority operation, you can move A here and then B here, and then you can move reserved row here, and then you can do a triple row activation and move the data from any of these to a destination over here. Okay, that's the idea. If you do majority, you do something different. Okay, let's go back, I guess. So that's the idea, basically. So the reason, you can keep going back. The reason why we want to have a separate part over here is because this is much cheaper to implement. Imagine the row decoder to enable triple row activation, right? You basically have a triple row activation command, and that goes to those three rows only and activates all of them directly. Whereas if you were operating directly on this array, this is, let's say, 512 of them. A, B, let's assume D is destination. A, B can be anywhere. How do you activate 2 rows that are anywhere, right? Or 3 rows that are anywhere? You need to do 3 rows activate, actually, C. Well, that's very tough now, right? Because you need to actually have 3 row decoders as opposed to a single row decoder. And we don't want that. That's very expensive. And that's why it makes sense to actually implement something that's very small over here with a very simple row decoder that's specialized for triple row activation. So this is the implementation of the ambit substrate. Okay, let's go back. So now this slide makes more sense. So you have designated rows for triple row activation. You have reserved row, and you do what I just said, basically. RowClone A into D1, B into D2, and RowClone R0 into D3. That's the mistake I had made on the board, but this is correct. If you want to do bulk AND, because bulk AND is 0. And you activate D1, D2, D3 using the simple row decoder, and then you RowClone the result into destination row C, which is at the top. Yeah. Hopefully that makes sense, right? Okay. So these all can be instructions in the ISA, or this bulk AND can be a special instruction by itself, and then that gets implemented in using these operations on the memory controller. Okay, beautiful. You can do bulk OR, bulk majority, and then add bulk NOT, bulk NOR, bulk NAND, etc. So the question is, how do you implement NOT? So majority is nice, AND and OR are nice, but alone, they're not complete. They're not functionally complete, right? You cannot implement a circuitry without having an inversion operation. So the good news is the inversion operation is actually already there. So if you have seen the circuitry, essentially, this is another way of looking at it, but maybe we go back to what I showed earlier quickly. So this is essentially the NOT, or the complement of a row of a bit, is actually on the other side of the sense amplifier, as you can see, right? This is, if you imagine if you activate only C, and we have seen this before. If you activate only one row, you sense the value of this at the top end of the bit line, but on the other end of the sense amplifier, other side of the bit line, let's say, you essentially have the complement of that value, right? Because of cross-coupled inverter. So you already have the NOT actually, but you don't have it in the same subarray. So in this paper, in the ambit paper, we proposed taking it and putting it into the same subarray with some complicated circuitry. Not terribly complicated, but it's a little bit disruptive into the DRAM design. So we have this additional dual contact cell where we can take the other end of the sense amplifier bit line bar and put it back into the capacitor, as you can see. And you can imagine how this is enabled, basically. After you get the data that you want, inverted data, inverted C, let's say, you have another special operation where you connect this N-word line, which is the data over here, to the capacitor over here. So there's some circuitry that's involved. But you can see that you need to create a path from this bit line bar, the other end of the sense amplifier, back into this subarray to a special row. And once the data is in that special row, you can copy it anywhere inside that subarray. That's the idea over here. It's a bit invasive to the DRAM design, and there's a lot of overhead over here, but later works improved on this. But the concept is there. So implementation is not perfect over here. But the big key idea is you can feed the negated value in the sense amplifier into a special row. Okay. Now, if you have this, you can actually improve. You can actually implement any operation after this, right? Because we have a NOT now. Oh, sorry. We have a NOT, and this is the throughput improvements of NOT and the energy reduction compared to moving the data out and doing the NOT and then writing it back. So you can see that there are significant benefits. NOT is actually the fastest, AND and OR, and then NAND and NOR builds on AND and OR and NOT. And clearly you can do XOR, XNOR, and you can do any operation after this, right? Except it's an interesting, it's operating using in a bulk bitwise manner. So if you think about it, you're operating on, let's say, 8 kilobytes at a time, 8 kilobits at a time, whatever the granularity of your row is. And you cannot do it at a smaller granularity. You can do it at a larger granularity across many subarrays. That's easy, but smaller granularity is hard. So you need to express your algorithms in a bulk bitwise manner. And this is actually a nice exercise. People normally don't write this way, but there are some workloads that happen to be very amenable to bulk bitwise execution. And in our opinion, anything can be written this way because now you have and or not, right? It's you're functionally complete. You just need to rethink your algorithm, data mapping, and maybe you sometimes need to pad the rows with zeros, etc., so that it's written in a bulk bitwise manner. Okay, but there are some algorithms that actually operate using a lot of bit vectors, bitmaps, for example. Databases use bitmap indices. I'm going to give you an example. That was the first thing that we targeted. People actually created databases to maximize bitwise operations, like Bitweaving database, which is an interesting database. The goal was to actually speed up the database using GPUs. That's why they wanted to actually maximize the bitwise operations. They didn't need GPUs, in my opinion, but they could have done it with FPGAs too. And then Microsoft wrote this Bitfunnel web search engine, which is also very bitwise. A lot of DNA sequence mapping, as we will see later on with near memory processing, is very bitwise. Encryption algorithms do a lot of bitwise operations. You can talk to Mayank in the back about that. And then set operations. Like if you represent set membership using bit vectors, you can do set union, set intersection. They're all bitwise operations essentially, which we're going to see with bitmap indices also. So there are some algorithms and workloads that actually heavily use bulk bitwise operations. But I think the potential is even larger. If you have this sort of substrate like this, how do you actually rethink your algorithm? Can you do machine learning using bitwise operations? And this is what people are doing today, actually. People are designing how to do a matrix multiplication, matrix vector multiplication, using this sort of bulk bitwise substrate. There are papers on that topic. So you can imagine new ways of doing things because your substrate is very good at that. Okay, so let me give you an idea of what we did initially. So this is a bitmap indices. And these are data structures that are used in many databases for fast queries, fast range queries and joins. You do many bitwise operations to perform a query base. So this is one way of representing different sets in a database. Let's assume that you're talking about your database contains a database of people, and you want to classify some ages. And these are maybe very commonly used categories for ages. And you have a bitmap. Let's assume that this is 8 billion people, smaller than the population of the world today, but close enough. Let's do 10 billion if you want. 10 billion people. One bitmap represents whether each person is under the age 18, right? Another bitmap represents ages 18 through 25. Another bitmap represents that. Another bitmap represents that. So that's age. And then another bitmap, another set of bitmaps may represent where do they live. Another set of bitmaps may represent, I don't know, their height, right? Another set of bitmaps may represent how much they earn. Another set of bitmaps may represent something else. And then you may want to do a range query that that tries to find the intersection of some things that you want to figure out. You want to find out people who live in Zurich, who are within some age range, who go to ETH, who study electrical engineering or something like that, right? And then you run this query. It's a lot of bitwise operations across many bitmaps that are huge. So this is an example application that actually is a great fit for this sort of bulk bitwise execution, right? Because the application is bulk bitwise itself. And now you map it to a bulk bitwise hardware, you get huge speedups. Hopefully this gives you an idea, right? Of course, not all databases are like this, but this is not an unreasonable way of designing a database. And people have designed databases this way. And yeah, we see significant speedups using bitmap indices with smaller number of users. These are the size of databases with some sort of queries, like 16 million users. As the database size increases, you get higher benefits. From, for example, 8 to 16 million, you get higher benefits. So basically, this sort of application fits nicely. And then there's a full database that is designed for this purpose. And we ran many queries. Again, this is all in simulation because we cannot really do this on a real system. But we'll talk about the real system later on. All in simulation, we see significant benefits of porting a database and running different queries. You can see the queries over there, some queries. You get significant performance improvements, again, on a real database. So this sounds good, right? Yeah. So this is the original paper where we introduced the AND and OR idea, and then we added NOT and a lot of evaluations for the AMBIT paper. For some reason, this was rejected 4 times, and I have no idea why. One of the reasons why this was rejected, I should probably collect these reasons so that I can talk about it more. It's actually in some of the backup slides for the older versions, but older versions of this course. But one of the reasons was, this is a very neat and nice idea. DRAM manufacturers will never implement it. Reject. That sounds like a great reason for rejection, right? It's wrong at many levels. One is, first of all, there are 2 reasons, I think. Did we discuss this before? I don't think so, yeah. I think first reason is, who cares if DRAM manufacturers will implement it? That's a very good attitude to have, actually, in research. Not everything needs to be implemented, in my opinion, right? Does a proof of a mathematical theorem, does it get implemented? How do you know if it's implemented or not? Why do people publish it? Should they not work on it? So if this is the mentality, then a lot of things in scientific pursuit should not be done unless it's implemented. This is a very bad mentality, I think. This is really destructive for science by people who think they're scientists. They think they need to be a lot more careful. That's one. That's one way of attacking this argument. The other way is actually maybe even worse, because the question to ask would be, how do you know? Right? Nobody knew about this. If this doesn't get exposed, you guarantee that no one will implement it. So how do you know that no one will implement it, right? So that's a very dangerous comment, I think. I think people need to be more careful when they make comments like this, but you can see, these are real comments. I can show you the real comment over there. DRAM manufacturers will never implement it, and as a result, it's rejected. So I think, anyway, if you review papers, keep that in mind. We need to be very open-minded. Our goal is to advance science, not necessarily require an implementation of an idea, even immediately or in the long term. Because the idea may lead to some other idea, and then idea may lead to some other idea, and then idea may lead to some other idea, and then that idea may lead to some other idea, and that may eventually get implemented, right? If you cut it at the source, you're guaranteeing that your self-fulfilling prophecy is true. And the second is, nobody has a crystal ball, and this reviewer should not pretend that they have a crystal ball, or they know better than everyone else in the world. Right? So, does this sound like fun? So there's also another lesson over here, which is you got to get ready for these comments, because there are all kinds of weird people in the world. Which means that if you're doing research, you need to have very sharp focus and you need to be resilient, right? Because you cannot control what other people say. That's true in general in life, actually. You cannot control what other people say, but you can control what your reaction to it is. You can say, this is stupid. Which is what I'm saying without saying that. But and then basically I believe in this idea, and let's see what happens, right? And then you basically are resilient and you keep publishing it. And Vivek did a great job doing that, for sure. Yeah. Okay. Sometimes we need to have a stupid button responding to reviewers. Yeah. Okay, anyway, I have more stories here, but let's move on. So there's a longer version of this in this longer chapter in DRAM bulk bitwise execution engine. Okay, let's talk a little bit more about how to make this easier to adopt. Because when we wrote the first paper, we didn't think about the adoption, right? And you cannot solve all of the issues in a single paper, unlike some reviewers want you to do. You cannot get it implemented right away, right? You write the paper and also get it implemented. That way you prove the reviewer wrong. That's a very tough thing. Impossible thing in some cases. So later we said, can we actually make this more, let's say, methodical and programmable, such that any application can benefit from it? And I'm going to give you the methodology over here. It's a framework, essentially. And the idea is we want to enable the implementation of any bulk bitwise operation. We're still bulk bitwise. We're not going to change that. Only bulk bitwise type of algorithms will benefit from it, and people need to rethink their algorithms if they want to. But essentially, if you want to do some sort of bulk bitwise convolution, for example, you specify it, or some sort of convolution, you specify it using this hardware logic. And anything you can specify that way, basically. It could be multiplication, it could be division, it could be convolution, it could be copy. You specify it using this sort of logic. And then we actually convert that to a majority inverter graph, what's known as a majority inverter graph. And that inverter graph, there are some electronic design automation tools that are developed for superconducting logic, actually, because it has a lot of majority operations in it. This is from EPFL, Nani de Michele's group, if you're interested in the paper as references. We use that to, let's say, reduce the height of that graph so that you can reduce the latency of the operations. And then we have a way of converting that majority inverter graph to a microprogram. That's very similar to what I showed you earlier. RowClone operations, triple row activation operations, that's essentially activate precharge. In the end, they also get translated to activate precharge operations. But RowClone, majority operations, not operation, or operation, and operation. This is a microprogram to execute that majority inverter graph that belongs to that instruction, desired operation, which could be anything, that as long as it's specified using that sort of hardware logic. And we store this microprogram, over there, associated with that bulk bitwise operation a new bulk bitwise operation somewhere. And when the program is augmented with this sort of instruction, again, it could be a bulk bitwise convolution, it could be a bulk bitwise division, that gets shipped to the memory controller. Memory controller fetches the microprogram and executes it according to the specification of the microprogram. All of those operations that I showed you earlier for bulk and is one example, right? And that's the idea. This way you can implement anything as long as you specify it using that and or not logic, and you think your algorithm such that it's bulk bitwise, such that it uses those operations. That's the idea. So this is a very general purpose framework, as you can see. And in the end, we look at different operations. You can see the paper. We look at different applications, including some neural networks that are not so wide in terms of bit width. We show in this paper, for example, if you want to do a multiplication using this way, it's bit serial multiplication. You can read the paper. I'm not going to go through the details, but it's fascinating. It's actually a very good thing to read. You need to do bit serial multiplication, and the latency of the multiplication is very long, actually. The latency of the multiplication is quadratic with the bit width of the multiplication. So if you're doing 1-bit multiplication, it's not that bad. But if you're doing 64-bit multiplication, it's pretty bad because you have quadratic latency. And the paper has like energy and latency of those operations. So this sort of substrate is much better fit for low bit width operations, where you're doing, let's say, 2-bit multiplication, 4-bit multiplication. Even 8 bits is a bit too much, maybe, sometimes, right? So later works actually try to optimize that, and maybe we'll cover in some cutting-edge research session. But in this work, we show that you can get significant performance energy efficiency improvements while making the substrate more programmable and more easily accessible for many people. Okay, that's a summary of, again, a detailed work. These are actually substantial amounts of work that for this to get accepted in a top conference, you need to do a really substantial amount of work. I'm covering this very quickly because there are a lot of ideas to cover. If you focus on one paper too deeply, then you won't get the higher level ideas, and you focus a lot more on the implementation, because implementations may change, but the ideas will remain, right? That's the key takeaway also from my thinking in this course. Okay, so that was SIMDRAM. More recently, Geraldo, who graduated recently from my group, his thesis was on this topic. Rahul was the next one. Geraldo is number 24. Rahul was number 25 to graduate. His thesis was on processing in memory. And this is one of his works in this area. And the idea is here, can we do this completely transparently to the program? And also, meaning an existing application, can we take it and completely transparently compile it into a processing using DRAM substrate that is capable of what we just discussed? And can we also do it in a more efficient way? This is a very quick summary of the entire work. Maybe I will not talk about this in detail. Maybe we'll get back to it. But okay, let me give you the idea. So, so far what we've seen is copying, initialization, majority, and not operations. They're all bulk bitwise, right? They operate on the entire row. And here we have a different way of looking at the row. So essentially, this is let's say this is your entire row. Even a row actually doesn't consist of a single array. It turns out there are multiple what's called mats in DRAM. And the reason is, if you want to activate 8 kilobytes, that's a very long word line. What people do is they have the row decoder connected to the word line, and there is a piece called a mat that is essentially activated through this part. And then there's another piece that's connected. There's a repeater essentially over here to amplify the signal so that you can maintain signal integrity in this huge word line. Essentially, there are repeaters over here that amplify the signal to a smaller sets of mats. These are small repeaters. So this is now we are going another level in the design. If we had started with this, then you would probably think there's a lot of complexity, but there's actually a reason for all of these design decisions that are made in DRAM. So internally, DRAM actually consists of smaller arrays called mats. Subarray is not the smallest unit. But these operations are working at the granularity of the entire row. They're mat unaware because DRAM operates that way. DRAM, actually, whenever you access an entire row, whenever you activate a row, all of those mats are enabled. Okay. So for example, if you do a bulk bitwise operation, these three, all of these are enabled simultaneously. Okay. So basically, these architectures are very wide, bit serial SIMD engines, 64K wide, let's say. That's one example. So what does this lead to? Essentially, this leads to some inefficiency because you have a large and rigid access granularity. And if you don't have that much parallelism, for example, you need to operate on only 512 bits of data. You're wasting a lot of bits over there, right? Essentially, this leads to throughput and energy waste. This second one I'm not going to talk about, but that's a different issue, which is if you want to do reduction operations. Like, for example, if you want to reduce the data that comes from different parts of a subarray, you don't have mechanisms to do that using DRAM, but we had some support for that in this work that I'm not going to talk about in detail. But essentially, there's also a third problem, which is a challenging programming model. Yeah, you don't have a compiler support. A compiler cannot easily get that high level of parallels, like 64K bits parallels. So this work targets these three problems. And let's take a look at actually what the programmer needs to do, because it's going to be important for next week's lectures. Let's assume that this is your high-level code. It looks bulk bitwise, assuming the size is large over there. It's basically comparing AI to some predicate I, and then if that's true, then it's computing AI plus BI. Otherwise, it's computing AI minus BI and setting CI accordingly. If these are large arrays, this is quite bulk bitwise. And you can actually implement this using DRAM with the operations that we discussed. But the data structures need to be aligned nicely inside the DRAM, inside the subarrays. Right? This is a programmer's task. Can you make it easier on the programmer? Going to be important. You need to identify the array boundaries. That's important. You need to manually unroll the loop. You need to map C to processing using DRAM instructions. You need to orchestrate data movement. So, and then you need to handle the conditional operations. That's also important. So in the end, the programmer needs to come up with something that looks like this. This is the assembly-like code that we have for processing using DRAM. You can see there's some initialization operations, and then there's some bulk bitwise addition, subtraction, bulk bitwise greater, bulk bitwise if and else computation. These are all implementable using bulk bitwise operations. Again, you can read the paper, look at the source code. Source code is all online also. But what the programmer wants to do is none of this. They just want to write their kernel. And they don't want to be aware of any of this, right? That's the general programmers in the world. So that's what the goal of this work is. Essentially, there's a large and rigid granularity that limits applicability, efficiency, and also it hurts compiler support, because compilers are not designed for very wide vectors today. They're really designed for small vectors. Even with small vectors, they're not very good. For example, if you want to take advantage of Intel's AVX instructions, they're automatic compilers that you can use. And these instructions are 512 bit wide. And still, a very limited set of workloads can be automatically compiled to take advantage of this. We're going to do that we're going to retarget that compiler to DRAM. But there's more opportunity than what this paper demonstrates, basically. Okay. So basically, what's the idea? Essentially, we want to enable fine-grained access to DRAM as opposed to entire row. Instead of enabling all of the mats when we activate a row, we want to enable a configurable number of mats. Ideally, the smallest one is 1 mat. Let's say it's 512 bits. But if we want, if our parallelism is greater than 512, we want to enable 2 mats. If it's greater than that, we want to enable 3 mats. Basically, we want to enable this configurability. So it looks like this, basically. If we have 2 mats level of parallelism, we want to enable only those 2 mats. So the problem is there's a global word line that propagates across all DRAM mats, even though it has some word line drivers, it's not segmented. So that's the DRAM mat, basically. So the idea is to use what's called as fine-grained DRAM. And the idea is to segment that global word line to access individual DRAM mats. So you have a segmented global word line, which essentially uses some sort of isolation. So this is not shown in this picture nicely, but you have an isolation transistor here, isolation transistor over here, isolation transistor over here, another isolation transistor over here. And you decide which isolation transistors to enable or disable. And if you enable the isolation transistor, you enable the word line to propagate to that mat. If you disable it, you ensure that the word line doesn't enable that mat. That's the idea. This is one design of fine-grained DRAM. There are many designs that people have proposed in the past. So this way, by enabling 2 isolation transistors for the initial 2 mats, you can actually enable only those mats. And actually, this fine-grained DRAM was proposed by multiple works in the past. And the idea is, the reason they propose is not because of what we envision over here, but their reason was, whenever you access DRAM, you activate 8 kilobytes of data, let's say, right? But sometimes you need only 8 bits, and the rest is useless. You don't have any locality, let's say. Then you're activating all this 8 kilobytes just to get 8 bits, right? Maybe sometimes even 1 bit. And people said that this is a waste. Let's try to design a more flexible DRAM architecture such that we activate much smaller and not waste energy. And there are many designs that look like this. In fact, we also have a design, more recent design, which we think is a bit cleaner than prior designs, sector DRAM. So you can take a look at it. So you can use any of those fine DRAM architectures to enable this, essentially. And if you do that, now you can enable only what you need, what is specified by the compiler or the programmer. And this now enables you to do operations on some other mats, right? When you do, for example, bulk bitwise, you're executing 1 microprogram or on 2 of these mats, and you start it. You start executing some other microprogram on some other mats. Right? This could belong to the same application or potentially to different applications if you have that sort of support. That's why we call this the multiple instruction, multiple data model, right? Different mats are operating on different instructions and different data. So it's kind of like a multiprocessor in DRAM. They're doing different things. Okay, as opposed to a single instruction multiple data processor, which is SIMDRAM, every mat is doing exactly the same thing on different data elements. Okay, so we also add some low-cost interconnects to reduce data, which I'm not going to talk about, but there's some DRAM design over here. And finally, but very importantly, we enable the SIMD parallelism in a DRAM mat to be on par with vector ISA SIMD width, because each DRAM mat consists of 512 columns. And that's essentially the width of a vectorizing compiler today that targets today, AVX, mainly because the existing SIMD operations and existing popular ISAs happen to be a maximum of 512 bits today. Of course, this may become better, but even 512 bits may be too much in some applications. It's good to think about that. Okay, so basically, in the compiler, transparently extracts SIMD parallelism and schedules these processing using DRAM operations while maximizing the utilization of DRAM as much as possible. So Geraldo implemented 3 new low-level virtual machine, LLVM, which is a compiler that's relatively popular today, passes targeting this execution. So there's automatic code identification. There's auto-vectorization that's done by LLVM. Again, this part is not, in my opinion, necessary. But if you want to do it completely transparently to the user, yeah, you need to do auto-vectorization, right? But in my opinion, auto-vectorization in the compiler is very limited today. People have not figured out the best ways of doing this. So if an algorithm designer actually goes and rethinks their code, a smart one, they can enable a lot more vectorizability in the code, because existing compilers are limited. They need to be safe when they vectorize code. And if the algorithm is not a good fit, the compiler cannot do much after that point, right? And then the compiler does code scheduling and data mapping to the DRAM mats. You can see there's some over there. It's all open source also. And then eventually generates a final binary that consists of essentially bulk bitwise operations and some memory allocations. Okay, I already said all of this, but you identify SIMD parallelism, generate put instructions, and set put is processing using DRAM, set the vectorization factor, and then, yeah, you improve SIMD utilization, and then you generate appropriate binary instructions for data allocation and put. There's a lot more to discuss. Actually, we're going to discuss this later on, next week especially. There are some other issues in execution of this, like we talked about data transposition. You do need to transpose the data actually, so that you can operate on the data in a vertical manner. But next week we're going to talk about that. Data coherence is a big problem in general in processing in memory. We're going to cover that. Address translation is always a problem. This is the hairiest problem that we have in computer systems today, in my opinion. Data allocation and alignment, etc. You can read the paper. And this paper compares to multiple works, as you can see. I will not go into a lot of these details in comparison, etc. But this is a summary on the workloads where it works really well. It's a very small set of workloads that can be auto-vectorized, of course. It's good to keep that in mind. But when it works well, it works really, really well. You can see that these are the energy efficiency improvements compared to a CPU and GPU. This is the entire execution of the workload. And here, the workloads are so parallel that every single DRAM cell is doing work. Hopefully, this will become more generalizable to other workloads as well. But that requires more work, in my opinion, and more innovation. Okay. So that's MIMDRAM. Yes. Yeah, like when you say 2 dimensions, what do you mean? Like you, instead of operating on one row, 1 bit at a time, you operate on multiple bits at a time, or what do you mean exactly? Huh? Oh, tile. Yeah. Yeah. I mean, yeah, you can map that tiling to this, but you cannot operate on an exact full tile, right? If you want to, for example, do a small matrix vector multiplication on a tile, you cannot do that directly with the substrate. You will need to change DRAM. And I would recommend thinking about solutions on how can you change the DRAM to enable that sort of thing. That's not possible today because of the substrate. The substrate is bulk bitwise essentially. Yeah, it doesn't have the tiled operation capability. We'll see later, like some other substrate like memristors, RRAM, phase change memory, you can do tiled sort of operation. Yeah. Yes. Yeah. Yeah. So we're going to look at that when we talk about processing near memory. Yeah, processing using memory is something we're focusing on today. But when we get to processing near memory, we'll discuss 3D stacked architectures. There needs to be more to be done in that domain, but all of these ideas are applicable to HBM as well. Because if you look at HBM, DDR, they're all internally the same. The array is the same in DRAM. So you can do all of these in HBM, plus you can do more because you have 3D stack connections across the memory arrays as well as the logic layer. Yeah. What do you mean, why don't we do that? Yeah, I think it's good to think about that, right? I mean, certainly if you have 3D stacking, that enables you to do better near memory processing. And there are some things that are not easy to do using DRAM. And you can actually move the data and do the near memory processing in the logic layer and then move the data back, right, to another layer potentially, right? So clearly 3D stacking enables, but that's near memory again, right? I don't know if it helps you to do better using memory. It's good to think about that. How can you take advantage of 3D stacking to all of those structures to actually do data movement, etc.? It's a good topic to think about. Yes. Yeah, I mean, certainly, like if you have very good cache locality and you need very expensive operations, yes, we're going to get to that also. Like these are some, like where should something be executed, basically? That's what you're getting at. Is there any reason to actually have a processor like today? And I think, yes, there are some very compute-intensive workloads with good locality, pieces of a workload that should not be executed on the memory side, in my opinion. Right? In the end, I think it boils down to how do you identify what should be executed where. We need very good metrics to enable that. If we can do that automatically, that'd be great. But we'll see some methods next week on how to decide what should be executed where. There needs to be more work in that area. But there are definitely some parts of a workload that should be executed in the processor because you cannot outperform. You cannot be any more energy efficient because you have such good locality, high compute intensity. A well-designed processor would do much better, but probably that processor doesn't need that much, that huge cache hierarchy. Right? So it can be much more efficient. Okay. Okay, maybe next week, Geraldo will talk about this. This is more recent work that tries to figure out what kind of algorithm for addition and multiplication should you use? What kind of bit precision should you use? How do you identify the bit precision you should use inside the DRAM? And how do you select, based on the bit precision you have, what kind of algorithm you should use? Because there are many multiplication and addition algorithms that you can use for this purpose. But I think we're going to go into more detail on this one. I think actually we should have a cutting edge research because this was published this year. And I think that this is the cutting edge at this point. There's more that needs to be done in this area. Okay. There are more works on programmability that we're going to cover next week. This is just for foreshadowing next week that I'm going to skip right now. But I think Geraldo will talk about a lot of these sometime. But I want to cover this before we part. Basically, all of these are very interesting, but everything is based on circuit theory, right? Spice simulations, first principles, and they all make sense if you think about it. The question is, can they be implemented? Right? That question should come after things are published, not before, for gating the publication of something, right? That should not be the bar to keep a publication. So more recently, people have discovered that existing DRAM chips can do a lot of things, actually. I've already given you the idea of compute DRAM. We've already discussed Pi DRAM, which we're not going to discuss. But I'm going to give you some more recent results. So this is last year. And in this work and another work, Ismail uncovered that existing DRAM chips can do a lot of operations, actually. So this is a summary of two works. The first one, we actually test a lot of DRAM chips, real DRAM chips. And we show that you can copy one row into up to 31 other rows with almost perfect success rate. Success rate, you can see the definition, but it's reliability essentially. You fail only on 0.02% of the bits. That's a very low fraction by violating the timing parameters. And again, the context is DRAM chip is not designed for this purpose. It's not supporting this operation. We're violating the timing parameter. We're abusing the DRAM chip in a sense to force it to do this operation. And it's still doing it almost perfectly. So that's the context, meaning RowClone is a almost already implemented idea. Now, if you go and change the DRAM chip, you can do much better, basically, than this. That's the idea. And we also show that you can perform NOT operation and also AND, NAND, OR, and NOR operations, which was not shown. Well, OR and NOR were definitely not shown before, but 16 input was also not shown before. So how do you do this? Basically, multi-row copy. You know RowClone, basically, by consecutively activating two rows, you copy the source row to the destination row, so everything becomes source. In multi-row copy, you consecutively activate one row, which brings data in the sense amplifier, and then you violate some timing parameters, which enables us to activate let's say, 31 other rows. So by violating the timing parameter in a very special way, you can actually activate a lot of rows concurrently in real DRAM chips. And the reason why this happens, we have a hypothesis of this in the works, because there's a hierarchical structure to the row decoder. There are some rows that also get connected at the same time, and they, if you actually violate the timing parameter, you don't give enough time for the circuit to settle, so they all become activated. And now you can copy one row to 31 other rows, so you can speed up the initialization or copying significantly. That's multi-row copy. NOT operation I've already given you, but we actually demonstrated in real DRAM chips right now. There's a NOT gate over here. Now you connect the rows in neighboring subarrays through a NOT gate by consecutively activating those. So you actually activate the source, which brings the data into the destination. And in quick succession, you activate the destination so that the destination row captures. Actually, this one doesn't bring the data into the destination. The first activation brings the data, senses the A bar over here. And if you are actually able to activate the destination in quick succession, the data gets captured in the other part of the sense amplifier. So that actually works also. And this is the most interesting part, maybe. If you activate 2 rows in quick succession, you can simultaneously activate multiple rows in neighbor subarrays. Well, this is a building block, basically. So you have neighboring subarrays that look like this, subarray X and subarray Y. They share some sense amplifiers. And you actually violate the timing parameters significantly. These are 2 real timing parameters, activate the precharge and precharge to activate. And you target the activates to 2 different rows over here. It turns out you can activate both of the rows. And it's not just 2, you can actually do 4, 8, etc. The paper has some examples. So now what happens? What can you do this? What can you use this for? So let's take a look at this picture over here. Here we have, okay, I'm going to use this one. Here we have 2 things on this end of the subarray and 2 things on this other end of the subarray. This is a different subarray, essentially. So if you actually violate the timing parameters and concurrently activate A, B, X, and Y, the question is what happens? So we're going to fundamentally, if you can concurrently activate A, B, X, and Y, what the sense amplifier would do is it would compare the average voltage of A and B to the average voltage of X and Y. That's circuit theory again. They're similar to what we have seen earlier, right? What the sense amplifier did earlier was if you activate 3 rows on top, it basically perturbed the top part. And then it compared the change at the top to what's at the bottom and then amplified that. So now we're activating things at the bottom also. So intuitively, from a first principle standpoint, the sense amplifier should compare AB to X and Y. Right? So if AB, average voltage of A and B is greater than X and Y, you should get 1 at the top. Otherwise, you should get 1 at the bottom. Makes sense, right? Or 0 at the top. Now, if you can manipulate the bitline voltages, you can express a wide variety of functions using this sort of primitive. Let's say let's say I call this the reference subarray. I have an animated version, but it's not here right now. But it doesn't matter. I think you can do the animation yourself because we built enough background over here. Let's say this is our reference subarray. Let's say we want to compute a function of X and Y. Assume that we actually set this reference voltage to VDD and this one to VDD over 2. And there's a way of doing that in real DRAM chips that I'm not going to go over. It was published by this work in Micro 2022, and we verified that it's actually working. It's in our open source workloads. Basically, the average voltage here is 3 VDD over 4. Now, for this compute subarray to compute a 1 at the bottom, this part of the this bit line, the average voltage of X and Y should be greater than 3 VDD over 4. Right? If that's not the case, this will compute a 0 over here. Right? Now, assuming that the only values the voltage of a cell can take is 0 VDD over 2 and VDD, the only case in which the average voltage of X and Y will be greater than 3 VDD over 4 is if and only if X and Y are both VDD, meaning X and Y are both 1. Right? Which means that this is an end function by definition, right? If and only if X and Y are 1, you get 1 in the compute subarray. Otherwise, you get 0 in the compute subarray, right? That's an end function. And by, again, by construction of the sense amplifier, you get the opposite value on the reference subarray. So the NAND of X and Y is actually on the reference subarray. You compute AND over here, and you compute NAND over here by setting the reference voltages this way. And you can compute NOR and OR as well, but I'm going to leave that to you. It's a very simple change. Okay, that's fun. Okay, so that's the idea, and this is very fascinating, I think. And this is also the first work that shows this. And it's not just theory, it's also practice, meaning by violating the timing parameters in real DRAM chips using our infrastructures that you have seen pictures of, in some set of chips, we can see this. Basically, not in all of the chips, because not all of the chips enable us to violate all the timing parameters the way we want. That would be nice, actually. That way we can experiment with the chips nicer, but not all manufacturers allow everything to be done to their chips. I wish they allowed more so that we can discover more things in their chips. But if you actually, for example, look at, I'll get to you later. If you actually look at multi-row copy, this is actually all manufacturers. That slide applies to some AND and OR. For multi-row copy, you get almost perfect reliability, regardless of the number of destination rows. For AND, OR, NAND, and NOR, you don't get perfect reliability. Your success rates are sometimes 50% or close to 50%, usually higher than 50%. In some cases, you get higher success rates, which is not bad. Especially, I think it's still fascinating given that these operations are not supported at all, right? So we see these functions in real DRAM chips. So if you want to do 16 input operations, you get reasonably high success rates, 94%. It's not perfect, of course. Ideally, we don't want 94%. Unless you buy into this approximate computing thing that was sold very, very heavily at some point. Oh, we should do approximate computing all the time. Well, I don't want my computer to be approximate, sorry. Especially when I'm flying up high over there, right? I want actually an exact computer that does the right thing. I don't want to approximately die. So it's good to think about that, basically. But the approximate computing was extremely hot at some point. I think there are some cases where it makes sense, especially if your application matches, but we got to be very careful. So in the end, the goal of this demonstration is to show that even if you do nothing to the DRAM chip, nothing to the interface, you just abuse it, violate the timing parameter with a memory controller, you still get these operations inside the DRAM chip. Now imagine what you can do if you actually went and modified that DRAM chip to do actual computation as opposed to abusing it. So there's impact on data pattern, there's variation. So you need to study a lot of things. And the paper studies a lot of things, but there's more studies to be done and potentially more functions to be discovered in DRAM chips. And this is the paper. Okay, you had a question. Yeah. Oh, okay. So for example, the manufacturer may ignore an activate command that comes too close after a previous activate command, right? That's very easy, actually. They just need to add additional circuitry to ensure that another activate doesn't happen while an activate is in progress, right? Exactly, yeah. Some manufacturers do that. I don't think it's necessary for them to do that because it limits, in my opinion, it limits the capability of their chips, right? Because they're not liable. They basically say, don't use the chips this way. It's already said that way. Why add another circuitry to prevent that, right? Because maybe someone will abuse your chip and discover new things and then write papers about it and show new capability. In fact, that's what this is about, basically. There's new capability that's shown in real DRAM chips. And after this, actually, a lot of manufacturers came to us and we are in discussions with many of them. And they're quite excited about the possibility of their chips doing more using this. So in my opinion, it's bad for them to not allow this, but they do it. They're afraid of things, let's say. Memory, so you should understand something about memory industry. I think memory industry is built on very tight margins and tight competition and a lot of fear of losing that competition, right? So if they feel like if they expose more and more internally from their chips, somebody will discover the vulnerabilities and bad things inside their chips. And if not the bad things, they fear that somebody will be able to understand how they do things internally and they will replicate it and they will do better than them. And then they will lose their already small margin. So that's the mindset is the real reason why they would reject something like this, basically. Yeah. Okay, good. Okay, so we're almost at time here, but this is the paper. This is the other paper that looked at simultaneous many row activation. I'm not going to cover that, but we will probably have another session that combines RowHammer with this multi-row activation and looks at what is the effect of RowHammer when you do multiple row activation. And the news is very bad. Things become much worse if you do multiple row activation. But these are real experimental studies that you can do. Yeah, I think I'm going to stop here. Any other questions? In the next week, we're going to continue with a little bit more processing using DRAM. And then we're going to go into processing near DRAM and memory. If there are no questions, then we're done. Have a good weekend, and I'll see you all next week.